Welcome, we're so happy you tuned in tonight. Before we get started, I'd love to know, where are you watching from? Drop it in the comments. Now, let's get comfortable and drift into deep, peaceful sleep together. The snowflakes are tiny crystals of frozen water that form in cold clouds, and tonight, as you settle into the softness of your pillow, you can imagine them beginning their journey far above the earth, where the air is cold enough to transform vapor into something solid and beautiful, something that will eventually drift down to touch the ground with the gentleness of a whisper. And these snowflakes, these small miracles of geometry and physics, they begin when water vapor in the air turns directly into ice, a process that scientists call deposition. Though you don't need to think about the technical name right now, you only need to understand that somewhere high in the atmosphere, invisible moisture is becoming visible crystal, becoming something you could catch on your mitten and examine for just a moment before it melts away. And this transformation happens without any liquid water in between. The vapor simply decides, under the right conditions, to become ice, to skip the liquid, stage entirely and move directly into the solid form that will define its brief existence as a snowflake. A snowflake usually starts as a very small ice crystal, sometimes forming around a tiny particle in the air, perhaps a speck of dust or pollen or some other microscopic traveller that has made its way up into the cold regions of the sky. And this particle, so small you couldn't see it without a microscope, becomes the seed around which the snowflake will grow, the nucleus that gives the water vapor something to cling to, something to organize around. And once that first bit of ice forms, once that initial structure takes shape, the snowflake begins its slow process of growth, adding molecule after molecule in patterns that seem almost deliberate, as if the snowflake knows exactly what it wants to become. Though of course it's simply following the invisible rules that govern how water freezes and how crystals form in the particular conditions of temperature and humidity that surround it in the cloud. As the crystal drifts through the cloud, it can collect more water vapor and grow, expanding outward from that tiny beginning, becoming more elaborate with each passing moment, though this growth happens so slowly that if you could watch a single snowflake form, you would need enormous patience. The kind of patience that comes naturally when you're falling asleep, when time seems to stretch and slow, and the urgency of the day falls away like snow sliding off a roof in the warmth of morning sun. And the snowflake doesn't hurry, it simply exists in the cloud, moving with air currents, sometimes rising, sometimes falling, always changing, always adding new structure to its form, and this gentle accumulation of molecules is happening right now. Even as you read these words, somewhere in the cold upper atmosphere, snowflakes are being born, are growing, are preparing for their descent to Earth. Snowflakes are not always perfect, and this is something worth remembering as you let yourself relax into the comfort of your bed, because many snowflakes are small, irregular, or clumped together. They don't all look like the paper cutouts you might have made in school, with their precise six-pointed symmetry and delicate branches. Instead, they come in countless forms, some broken, some simple, some so small they're barely more than tiny ice particles, and yet each one is still a snowflake, still part of the gentle phenomenon of snow falling from the sky, still contributing to the soft white blanket that can transform a landscape overnight. And there's something deeply comforting in this imperfection, this variety, this acceptance that not everything needs to be flawless to be beautiful, that the irregular snowflake settling on the ground beside the perfect one is equally valid, equally worthy of existence. The classic star-shaped snowflake is one common form but not the only form, and when you think of snowflakes you might picture those six-pointed stars with their elaborate branches and sub-branches, the kind that appear on holiday decorations and winter greeting cards. And while these stellar dendrites do exist in nature, they represent just one possibility among many, one way that water vapor can arrange itself into ice, and the fact that this particular form has captured human imagination so thoroughly speaks to something in us that loves symmetry and pattern, that finds peace in the repetition of similar shapes, that can look at a snowflake and see both complexity and order existing together in perfect balance. And tonight, as your breathing slows and deepens, you can appreciate that balance without needing to understand all its intricacies. You can simply let the image of a six-pointed snowflake drift through your mind like the real thing drifting through cold air. Snowflakes can be thought of as little records of the air they travelled through, tiny historians that carry in their structure the story of their journey from cloud to ground, and this is a beautiful way to understand them. to see each crystal as a kind of frozen diary, its shape determined by every pocket of warm air it encountered, every region of high humidity, every moment of rapid growth or slow accumulation. And just as you carry within you the experiences of your day, the conversations you had, the sights you saw, the feelings that moved through you, the snowflake carries within its structure the atmospheric conditions it experienced, and unlike you, who might forget the details of an ordinary Tuesday afternoon, the snowflake holds its history in its very form, unchangeable until it melts, a permanent record of a unique path through the sky. They grow while gently falling, like tiny structures built in slow motion. And if you could shrink yourself down and watch this process up close, you would see something remarkable. You would see water molecules finding their places on the growing crystal, clicking into position as, if guided by invisible hands, you would see branches extending outward, reaching into the surrounding air, capturing more vapor, becoming more elaborate. And all of this would happen with a slowness that matches the pace of sleep approaching, matches the way your thoughts are beginning to slow down now, becoming less sharp, less urgent, more willing to simply drift and observe rather than analyze and plan. And the snowflake doesn't worry about its destination, doesn't calculate how long it will take to reach the ground. It simply grows and falls, existing fully in each moment of its descent. Snow in the air can be quiet because crystals fall softly and scatter sound. And this is one reason why a world filled with falling snow feels so hushed, so removed from the usual noise of daily life. Because the snowflakes themselves are absorbing and redirecting sound waves, creating a kind of gentle acoustic blanket that wraps around everything. And when you walk outside during a snowfall, you might notice how distant sounds seem muffled, how your own footsteps sound different, how even your voice seems to carry less far than usual. And this acoustic quality contributes to the sense of peace that snow brings, the feeling that the world has decided to slow down, to speak more softly, to move with more deliberation. And you can bring that same quality to your thoughts now, letting them become quieter, gentler, less insistent, more willing to simply settle like snow settling on a field. A calm way to picture snowflakes is as small pieces of geometry floating down through cold air, tiny mathematical problems solving themselves without any conscious effort. And there's something deeply relaxing about this image, about the idea that beauty and order can emerge from simple rules applied again and again, that you don't need to force or control or manage every outcome, that sometimes the best results come from simply allowing natural processes to unfold, and as you lie here in the darkness or soft light of your room, you can let go of the need to direct your thoughts. You can let them float and settle like snowflakes, trusting that they will find their own patterns, their own arrangements, their own gentle resolution into rest. Many snow crystals show six-sided or hexagonal symmetry, and this is perhaps the most famous fact about snowflakes, the characteristic that makes them immediately recognizable, even to someone who has never seen snow in person. And this six-sided nature appears again and again in snow crystals of all different types, from simple hexagonal plates to elaborate stellar dendrites, from hollow columns to capped columns, the number 6 recurring like a gentle insistence, like nature saying this is how water wants to arrange itself when it freezes. This is the pattern that feels most stable, most natural, most true to the fundamental structure of the water molecule itself, and you can count to 6 slowly now if you like, marking each number with a slow breath. 1, 2, 3, 4, 5, 6. And then beginning again, finding in this simple counting the same kind of peaceful repetition that the snowflake finds in its hexagonal structure. This six-sided symmetry comes from how water molecules arrange themselves when they freeze into ice. And to understand this, you need to imagine the water molecule itself, which consists of one oxygen atom bonded to 2 hydrogen atoms, forming a shape like a very shallow V. And when these molecules come together to form ice, they arrange themselves in a particular way, forming a crystal lattice that naturally creates hexagonal patterns. And this isn't a choice the molecules make, it's simply the most stable configuration given the angles of the bonds between atoms, the most efficient way to pack together while maintaining the proper distances and orientations. And there's something wonderful about this, about the fact that the visible 6-pointed snowflake is simply the large-scale expression of molecular geometry, the macro reflecting the micro, the pattern visible to your eye being the same pattern that exists at a scale far too small to see. In solid ice, Water molecules form a repeating pattern that naturally has six-fold structure, and this repeating pattern is what makes ice a crystal rather than an amorphous solid, because a crystal is defined by this kind of long-range order, this repetition of the same arrangement over and over, creating a structure that extends in 3 dimensions, and when you hold an ice cube in your hand, you're holding billions upon billions of water molecules all arranged in this same hexagonal pattern, all following the same rules, all contributing to the solidity and structure of the ice. And the snowflake is simply ice that formed in the air rather than in your freezer. Ice that had the freedom to grow in more elaborate shapes because it wasn't confined by the walls of an ice cube tray, ice that could express the full potential of water's hexagonal tendencies. That underlying structure influences how crystals grow outward, because as water vapor molecules land on the surface of the growing crystal, they tend to attach at positions that continue the hexagonal pattern, that fit naturally into the existing structure. And this means that the crystal grows in directions that are predetermined by its internal geometry. It doesn't grow randomly in all directions, but instead extends preferentially along certain axes, creating the arms and branches that we associate with snowflakes. And this growth is not planned or guided by any external intelligence. It's simply the natural result of molecules finding their most stable positions, of the laws of physics and chemistry playing out at the microscopic scale, and the beauty that results is entirely accidental, entirely unintentional, entirely the product of simple rules followed faithfully. Snowflakes often have 6 arms because growth tends to repeat in 6 directions, and if you could look at a snowflake from above straight down onto its flat face, you would see these 6 arms radiating out from the center like the spokes of a wheel, evenly spaced 60 degrees apart, and each arm grows under essentially the same conditions as the others, at least initially, because they all extend from the same central crystal, they all experience the same temperature and humidity, they all have access to the same water vapor, and this is why the arms often look similar to each other, why the pattern on one arm is often mirrored on the others, creating the symmetry that makes snowflakes so visually striking, though as we'll see later, this symmetry is rarely perfect, and the small differences between arms are part of what makes each snowflake unique. The arms can branch as the snowflake grows and changes conditions, because as the crystal falls through the cloud, it might encounter pockets of air with slightly different temperature or humidity, and these changes can trigger new growth patterns, can cause side branches to sprout from the main arms, can create the elaborate tree-like structures that characterize some of the most beautiful snowflakes, and these branches follow the same hexagonal rules as the main arms. They maintain the same angles, the same geometric relationships, but they add another layer of complexity, another level of detail, and a snowflake with multiple levels of branching can become extraordinarily intricate, a tiny masterpiece of natural engineering that existed for perhaps an hour before melting, a brief flowering of ice in the cold air. Even when a snowflake looks uneven, its basic structure often reflects that 6-fold tendency, because while perfect symmetry is rare in nature, the underlying preference for hexagonal organization remains, and you might see a snowflake where one arm is longer than the others, where one side has more branching, where the overall appearance is lopsided or irregular, and yet if you look closely you can still see the 6-sided foundation, the hexagonal core from which everything else grew, and this persistence of structure even in imperfection is another lesson the snowflake offers, another gentle reminder that you don't need to be flawless to maintain your essential nature, that irregularity and identity can coexist peacefully. The 6-sided pattern is a calm example of nature preferring order in certain conditions, and there's something deeply soothing about this idea, about the notion that the universe has preferences, that given the right circumstances certain patterns will emerge naturally, reliably, repeatedly, and you don't need to create this order yourself. You don't need to impose it through effort or will. You simply need to provide the right conditions and the order will arise on its own. And in the same way, you don't need to force yourself to sleep. You don't need to wrestle your mind into submission. You simply need to create the right conditions, a comfortable position, a quiet environment, a willingness to let go. And sleep will come naturally, inevitably, following its own internal logic, just as water follows its hexagonal structure. This kind of repeating structure is common in many crystals, not just ice, because the tendency toward order, toward pattern, toward symmetry is fundamental to how matter organizes itself at the molecular level, and you can find hexagonal patterns in graphite, in certain minerals, in the cells of a honeycomb, and you can find other symmetries, cubic, tetragonal, orthorhombic, in other crystals, each one expressing the particular geometry that its constituent atoms or molecules prefer, and this universality of crystalline order suggests something profound about the nature of reality, about the deep mathematical patterns that underlie physical existence. But you don't need to think about such large questions now. You can simply appreciate the beauty of pattern, the peace of repetition, the comfort of knowing that even at the smallest scales, nature organizes itself into structures that make sense. Snowflakes show that simple rules can create intricate beauty without effort, and this might be the most important lesson they offer, the insight that complexity doesn't require complexity, that you can start with something incredibly simple, water molecules and hexagonal lattice structure and varying conditions of temperature and humidity, and end up with something breathtakingly intricate, something that looks designed, something that carries an aesthetic appeal that humans find compelling, even though no human had any hand in its creation. And this emergence of beauty from simplicity is happening all around you, all the time, in the patterns of leaves on a tree, in the spiral of a seashell, in the branching of rivers across a landscape, and you are part of this same universe, subject to the same principles, capable of the same kind of effortless unfolding if you can just relax enough to allow it. Snowflakes often grow by adding water vapor molecules directly onto their surfaces, and you can imagine this happening molecule by molecule, each one finding its place on the crystal, guided by the electromagnetic forces between atoms, settling into position with a tiny release of energy, a tiny click of connection, and then becoming part of the structure, part of the growing whole. And this addition happens continuously as long as the snowflake remains in conditions where water vapor is available and the temperature is low enough for freezing, and the snowflake doesn't distinguish between one molecule and the next, doesn't choose which ones to accept. It simply provides a surface where water vapor can transition from gas to solid, and the molecules that land stay, and the ones that don't land continue drifting through the air until they find some other surface or some other snowflake. The growth happens more easily at edges and corners where molecules can attach more readily, because these locations offer more bonding opportunities, more places where an arriving water vapor molecule can form connections with the existing crystal structure. And this is why snowflakes tend to develop arms and branches rather than growing uniformly in all directions, because the edges and corners grow faster than the flat faces, extending outward while the center remains relatively thin. And this preference for edge growth is another simple rule that contributes to the complex forms we observe, another example of how local interactions, a water molecule and a crystal edge, can create global patterns, large-scale structures that emerge from countless small decisions made at the molecular level. As a snowflake falls, it moves through slightly different pockets of temperature and humidity. Because the atmosphere is not uniform, it's layered and varied, with warmer regions and cooler regions, wetter areas and drier areas, all mixing and shifting in response to larger weather patterns, and the snowflake drifts through this varying environment like a boat on a river, carried by currents it cannot control. And each pocket of air it encounters can influence its growth, can change the rate at which molecules add to its structure, can favour certain types of growth patterns over others. And this journey through varying conditions is one of the main reasons why snowflakes are so diverse. Why even snowflakes that form in the same cloud at the same time can end up looking quite different from each other. Those small changes can influence how quickly different parts grow. So if a snowflake passes through a region of high humidity, it might experience a burst of rapid growth, with molecules adding quickly to all its surfaces, but especially to those active edges and corners, extending the arms and creating new branches. And then, if it moves into a drier region, growth might slow or even stop temporarily, allowing the snowflake to simply drift without changing. And then as conditions shift again, growth resumes, perhaps in a different style, creating a kind of visual record of the snowflake's path through the cloud. And if you could read this record like reading tree rings, you could reconstruct the journey, could map out the various atmospheric conditions the snowflake encountered. Though in practice, snowflakes are so small and their journey so complex that this kind of precise reconstruction would be nearly impossible. When conditions favour rapid growth, branches can become more elaborate, because the fast addition of molecules creates opportunities for instabilities, for small variations in the surface to be amplified, for side branches to sprout from main branches, for the snowflake to develop that fern-like or tree-like quality that makes some crystals so visually striking. And this rapid growth is like creativity flowing without resistance, like ideas coming faster than you can write them. Down, like those moments when everything seems to work effortlessly, and the results exceed what you consciously intended. And just as you can't force these moments of flow, but can only create conditions where they're more likely to occur, the snowflake can't force its own elaborate growth, but simply responds to the conditions it finds itself in. When conditions are calmer, growth can be more compact and simple, producing snowflakes that are less ornate but no less beautiful in their own way. Small hexagonal plates or short stubby columns, forms that speak to restraint rather than exuberance, to quiet rather than flourish. And there's a place for both kinds of beauty, both the elaborate and the simple, and neither is superior to the other. They're just different expressions of the same fundamental process, ice crystals forming in the air. And in your own life, you might notice the same alternation between complexity and simplicity, between times when everything feels intricate and interconnected and times when things feel more straightforward and direct. And both modes have their value. Both contribute to the full texture of existence. Some snow crystals grow into thin plates, flat hexagonal structures that look like tiny tiles or windows, transparent or translucent depending on their thickness. And these plates form when temperature and humidity conditions favour growth on the flat faces rather than along the edges. When the rules that usually cause branching are temporarily suspended, and the result is a crystal that extends primarily in 2 dimensions rather than 3, creating a delicate disk of ice that catches light in particular ways, that can seem to glow with a soft inner luminescence when the sun shines through it. And these plate crystals are less famous than the branching dendrites, but they're equally common, equally beautiful in their geometric precision, equally valid as expressions of how water vapour becomes ice. Others grow into long columns or needles, extending primarily in 1 dimension, creating ice structures that look like tiny pillars or rods, and these form under different temperature and humidity conditions than plates, conditions that favour growth along the vertical axis of the hexagonal structure rather than outward from the centre. And a needle crystal can be surprisingly long relative to its width, a slender spike of ice that seems fragile but is actually quite stable given its size. And when many needles fall together, they can create a particular type of snow that feels different on your skin, that accumulates differently on the ground, that reflects light differently than other kinds of snow, and the variety of forms continues to unfold, continues to surprise even scientists who have studied snow for decades. Many snowflakes that fall are actually clusters of crystals stuck together, because as crystals descend through the cloud, they can collide with each other, and if conditions are right, if temperatures are near freezing and the crystal surfaces are slightly sticky with liquid water, they can adhere on contact, forming aggregates that can contain dozens or even hundreds of individual crystals. And these clusters are what we often see as large snowflakes during a snowfall, those big fluffy flakes that drift down slowly and settle on your coat sleeve where you can try to examine them before they melt. And while a cluster lacks the geometric perfection of a single crystal, it has its own kind of beauty, a more chaotic and organic quality, a reminder that order and randomness often coexist in nature. The overall process is quiet and steady, water vapour becoming structure 1 molecule at a time, and there's something profoundly calming about understanding this, about realising that the snowflakes falling outside your window right now, if it's snowing where you are being built by a process so gradual, so patient, so utterly without hurry, and the snowflake doesn't announce its progress, doesn't celebrate each new molecule that joins its structure. It simply continues, 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 and eventually this quiet accumulation results in something visible, something you can see and touch and appreciate. And in the same way, your journey towards sleep is quiet and steady. Your consciousness slowly releasing its grip on wakefulness, your body gradually settling into deeper relaxation, your breathing becoming slower and more regular. And you don't need to force this process, you simply allow it, trust it, let it unfold at its own pace. Temperature strongly affects the type of snow crystal that forms, and scientists have mapped out how different temperature ranges produce different forms, creating diagrams that show which shapes are most likely at which temperatures. And this relationship between temperature and form is remarkably consistent, so that if you know the temperature in the cloud, you can predict with reasonable accuracy what kinds of crystals will form there. And this predictability is another aspect of the order underlying snowflake formation. Another way that simple rules create reliable outcomes, and temperatures just below freezing tend to produce certain shapes. Temperatures around -5 degrees Celsius produce others, temperatures around -15 degrees produce still others, and this pattern continues across the range of temperatures cold enough for snow formation. Humidity, which reflects available water vapour, also influences growth style, because a crystal growing in very humid air has access to more water vapour molecules and can therefore grow more quickly and elaborate than a crystal in drier air, and the combination of temperature and humidity creates what scientists call a parameter space, a kind of map where each point represents a different set of conditions and produces a characteristic type of crystal, and snowflakes forming in different parts of this parameter space will look different from each other even if they're falling from the same storm system, even if they land side by side on the ground. And this sensitivity to conditions is part of what makes snowflakes so variable, so difficult to predict in specific detail, so endlessly fascinating to observe. Certain temperature ranges favour plate-like crystals, those flat hexagonal forms we discussed earlier, and this happens because at these particular temperatures, the physics of ice growth favours expansion in the horizontal plane, favours the addition of molecules to the flat faces of the hexagonal structure rather than to its edges. And scientists don't fully understand all the reasons why this happens, why certain temperatures produce certain forms, but they've observed the pattern reliably enough to document it, to create those diagrams showing which temperatures favour which shapes. And this is often how science works: observation preceding complete understanding, pattern recognition coming before full theoretical explanation. And there's a lesson here about accepting what you can observe even when you can't fully explain it, about trusting your experience even when the underlying mechanisms remain mysterious. Other ranges favour column-like crystals, those needle and pillar shapes that extend primarily in one direction, and these form at temperatures where the vertical axis of the hexagonal structure grows more readily than the horizontal plane, where the physics of molecular attachment somehow favours one direction over another. And again, the exact reasons aren't completely understood, but the pattern is clear and reproducible, and columns tend to form at temperatures both warmer and colder than the range where plates dominate, creating a kind of alternation as you move through different temperature zones, plates giving way to columns giving way to plates again, a rhythmic variation that reflects some deep property of how ice crystals grow. Some conditions produce needle-like crystals, particularly long thin structures that look almost like ice hairs or ice fibres, and these needles can be remarkably elongated, sometimes 100 times longer than they are wide, and they form under specific combinations of temperature and humidity, conditions that encourage vigorous growth along the vertical axis while limiting growth in other directions. And when many needles fall together, they create a type of snow that has a distinctive texture, that feels slightly different when you pick up a handful, that compresses differently than other types of snow. And if you've spent enough time in snow, you might have noticed these differences without necessarily understanding their cause, might have recognised instinctively that snow isn't always the same, that it comes in varieties that feel and behave differently. Dendrites, the classic branching snowflakes, form in particular cold and moist conditions, typically when temperatures are around -15 degrees Celsius and humidity is relatively high, and these are the conditions that allow the elaborate branching structures to develop, that give the snowflake enough building material to extend those long arms and create those delicate side branches that produce the forms we think of as quintessentially snowflake-like. And dendrites are perhaps the most photogenic of snow crystals, the ones that appear most often in close-up photography, the ones that seem to capture the essence of winter's crystalline beauty, and yet they represent just one small region of that parameter space we discussed, just one possible outcome among many, special but not more valid than any other form. Because the atmosphere is always changing. A snowflake's path is like a gentle journey through different rooms of air, each room with its own temperature and humidity, its own characteristics that will influence growth, and the snowflake moves from room to room passively, carried by air currents, unable to choose its path or control its environment, and yet this passive journey creates active growth, creates change, creates the accumulation of structure that transforms a tiny ice crystal into a complex snowflake. And there's something to learn from this passivity, this willingness to be moved by forces larger than yourself, this acceptance that you don't always need to control outcomes but can sometimes simply allow yourself to be carried, trusting that the journey itself will create something meaningful. This is one reason snowflakes tend to look unique, because even snowflakes that form in the same cloud, in roughly the same region, will follow slightly different paths, will encounter slightly different sequences of temperature and humidity, will experience their own individual journey that will be reflected in their final form. And while two snowflakes might look similar, might share general characteristics, the precise details of their structure will differ, will carry the signature of their particular path. And this is why the saying "no two snowflakes are exactly alike" has persisted, because even though it's nearly impossible to verify, you would need to examine every snowflake that has ever fallen, which is obviously impractical. It captures something true about the enormous variability of snowflake forms and the sensitivity of crystal growth to environmental conditions. The idea that no two snowflakes are exactly alike is a poetic way of describing immense variation, and while it's theoretically possible that two very simple snowflakes, two small hexagonal plates with minimal elaboration, might be indistinguishable from each other, the probability decreases rapidly as snowflakes become more complex, as they develop more branches and sub-branches, as they grow larger and accumulate more structure, because each additional feature represents another opportunity for variation, another way that small differences in growth conditions can create visible differences in form. And for a large elaborate dendrite with multiple levels of branching, the number of possible distinct forms is so vast that the likelihood of two identical examples becomes vanishingly small, not impossible, but so improbable as to be effectively impossible. Even if some crystals look similar, tiny differences in their growth history can make them distinct, because what we see when we look at a snowflake is the cumulative result of thousands or millions of molecular scale events, each one adding a tiny bit to the overall structure. And even if two snowflakes grow under nearly identical conditions, random variations at the molecular level, a water vapor molecule landing at a slightly different angle, a brief fluctuation in temperature, a momentary change in air movement, can create differences that propagate and amplify as growth continues, leading to structures that diverge increasingly over time, and this sensitivity to initial conditions is characteristic of many natural systems, this property where small differences at the beginning can lead to large differences in the end. The snow we walk on is made of many crystals piled together, countless individual snowflakes that have fallen and landed and accumulated into a layer that might be an inch deep or a foot deep or several feet deep, depending on how much snow has fallen and how recently. And each crystal in this layer started as a tiny ice seed in a cloud, grew during its descent, landed on the ground or on other snow crystals, and now sits waiting to melt or to be compressed by additional snow, or to be disrupted by wind or by your footsteps walking across it. And there's something marvellous about this, about the idea that the snow you see is actually an enormous collection of individual structures, millions or billions of separate crystals that happen to be close together but remain distinct, at least until they start to change through melting and refreezing and mechanical compression. Fluffy snow often forms when crystals are light and temperatures are cold, because at very cold temperatures the crystals tend to maintain their delicate branching structures without melting, without sticking together too firmly. And when such crystals accumulate, they create a snow layer with lots of airspace between individual crystals, lots of gaps and pockets that make the snow light and airy and easy to compress. And this is the kind of snow that's ideal for skiing, that makes that satisfying squeaking sound when you walk on it in very cold weather, that you can blow off your car windshield without much effort. And if you've experienced this kind of snow, you know the particular quality it has, the way it seems almost weightless, almost ethereal, barely there despite being visible and white and clearly real. Wet, sticky snow happens when temperatures are closer to freezing, near that boundary where water wants to be liquid rather than solid, and at these warmer temperatures the surfaces of snow crystals can have a thin layer of liquid water on them, or the crystals can be partially melted, and this liquid water acts like glue, allowing crystals to stick together more readily, creating larger clumps, creating snow that packs well for snowballs, that's heavy to shovel, that makes good snowmen because it holds its shape when you pile it up. And this is a different kind of snow than the cold, fluffy variety. Heavier and denser and more cohesive, and both types have their place. Both create their own experiences and possibilities. When snow is slightly melted, crystals can stick together more easily, and you can observe this yourself if you've ever watched snow falling, when the temperature is right around freezing, because you'll see those large wet flakes we mentioned earlier, aggregates that might be half an inch or even an inch across, huge compared to individual crystals, and these form because the slight melting makes the crystal surfaces sticky And when crystals collide in the air, they adhere, and as this process continues, multiple crystals merge into a single falling mass. And when this kind of snow accumulates, it settles quickly, compacting under its own weight, creating a dense, heavy layer rather than the light, fluffy accumulation you get with colder snow. Fresh snow has many air pockets, which can make it good at insulating the ground, because air is an excellent insulator. It doesn't conduct heat well, and when you have millions of tiny air spaces trapped between ice crystals, you create a blanket that slows the transfer of heat from the ground to the cold air above. And this insulating property is important for many animals and plants, because it means that the soil under the snow can remain warmer than the air temperature, can stay above freezing even when the air is well below freezing, providing a refuge for small creatures, protecting plant roots from extreme cold, creating a relatively stable microenvironment despite the winter, harshness above. And this is one of snow's many ecological roles, one of the ways it functions as part of the larger environmental system. Those air pockets can also make footsteps sound softer, because sound waves travelling through the snow get scattered and absorbed by all those air-ice interfaces, all those boundaries between different materials, and this scattering reduces the intensity of sound, dampens echoes, creates that muffled quality we associate with snow-covered landscapes, and when you walk on fresh snow you're compressing those air pockets, forcing air out from between the crystals, and sometimes this happens slowly and quietly, and sometimes it makes sounds, those creaks and squeaks that cold snow produces, the sounds of crystal structures breaking and rearranging under pressure, and these acoustic properties of snow are part of what makes a snowy landscape feel so different from the same landscape without snow, part of what makes winter sound like winter. Snow can look bright because ice crystals scatter light in many directions, and unlike a smooth surface that reflects light in one specific direction, creating glare or mirror-like reflections, snow crystals with their complex shapes and multiple faces reflect and refract light in many directions, sending it scattering in all directions more or less equally. And this diffuse reflection is what makes snow look white rather than transparent like a single ice crystal might look, what makes it bright, what makes a snow-covered landscape seem to glow with reflected light. And this property is strongest when the sun is shining but remains even under clouds, even at night when there's any ambient light at all to reflect. Even at night, snow can seem to glow because it reflects ambient light, light from the moon if the moon is out, light from stars, light from distant streetlights or building lights, light from sources you might not consciously notice but that are nevertheless present, illuminating the sky with a faint background glow, and the snow takes this faint light and reflects it, makes it visible, turns the landscape into something you can navigate even without a flashlight. And many people who have walked through fresh snow at night know this experience, this sense of the world being lit from below. The snow providing its own illumination, creating a kind of inverse of the usual daytime relationship where light comes from above. A snow-covered landscape often feels quieter because snow absorbs and scatters sound, as we've discussed, but also because snow tends to fall during stable atmospheric conditions that reduce wind and other noise sources, and because the presence of snow changes human activity, makes people move differently, speak more softly perhaps, creates an atmosphere that encourages quiet. And all these factors combine to make a snowy world feel hushed and peaceful. And you can bring this quality into your bedroom now, into your body and mind, letting yourself feel hushed, peaceful, quiet, allowing the metaphor of snow to extend into your inner landscape, blanketing your thoughts, softening your mental environment, creating space for rest. Snow can make a familiar place feel gently new, like a soft blanket laid over everything. And if you've ever looked out your window after a nighttime snowfall and seen your neighbourhood transformed, you know this feeling. The way familiar shapes become softened and simplified, the way colours become muted, the way the whole scene takes on a dreamlike quality, as if you've woken up in a slightly different version of your world, a quieter, cleaner, more peaceful version. And this transformation is temporary. You know the snow will melt eventually, but while it lasts, it offers a kind of visual reset, a chance to see familiar things with fresh eyes, and sleep offers something similar, a chance to reset, to wake up tomorrow with a perspective refreshed by rest, able to see your life and its challenges with new clarity. Snow crystals can hint at the temperature and moisture conditions in the cloud, and scientists who study snow have learned to read these hints, to look at a snow crystal and make educated guesses about the atmospheric conditions that produced it, because the relationship between conditions and crystal form is consistent enough that form serves as a kind of code, a visual language that speaks about temperature and humidity and air currents. And while you don't need to learn this language to appreciate snowflakes, there's something appealing about the idea that each crystal carries information, that it's not just beautiful, but also informative, not just decorative, but functional, a tiny weather report falling from the sky. Scientists classify snow crystals into many types based on shape, and over the years researchers have developed elaborate classification systems that recognize dozens of distinct forms, from simple hexagonal plates to complex combinations of plates and columns, from solid crystals to hollow crystals, from single crystals to aggregates. And these classification systems reflect the enormous diversity of snow crystal forms, while also highlighting the patterns and regularities that exist within that diversity, the way certain forms recur reliably under certain conditions, the way nature explores the space of possibilities systematically rather than randomly. And this systematic exploration creates both variety and order, both uniqueness and predictability. Careful observation can reveal plates, columns, needles, and more complex forms, and if you're willing to spend time looking closely at snow, perhaps using a magnifying glass or a dark piece of cloth to see crystals against a contrasting background, you can begin to distinguish these different types, can start to recognize the characteristic features of each form, and this kind of close attention can be meditative, can quiet your mind in the same way that any sustained focus on natural detail tends to quiet the mind, and many people find that examining snowflakes up close creates a sense of wonder, a renewed appreciation for the intricacy of the natural world, a reminder that beauty exists at every scale if you're willing to look for it. Snow crystal growth can be influenced by how much time the crystal spends in the cloud, because a crystal that forms high in the cloud and has a long fall to the ground has more time to grow than a crystal that forms lower down, and more time generally means more growth, means more opportunity to develop elaborate structures, to accumulate mass, to express the full potential of whatever conditions it's growing in. Though this relationship isn't absolute, because a crystal can also fall out of the cloud into drier air where growth stops, and in that case a long fall doesn't equal more growth, but rather equals more time drifting without change, simply waiting to reach the ground. Strong winds can break delicate branches or cause crystals to collide and clump, because snowflakes, despite being ice, are fragile, especially the elaborate branching dendrites with their thin extended arms. And when wind speeds are high, these delicate structures can be damaged, can have their finest details broken off, can collide with other crystals with enough force to shatter and fragment. And this is one reason why very windy conditions tend to produce less photogenic snow, less of those perfect crystals you might photograph, and more of broken fragments and irregular pieces. But even broken snowflakes are still snowflakes, still part of the snow that accumulates, still contributing to the white landscape. And there's no judgment in this, no sense that broken is worse than whole, just different, just another state of being for ice crystals falling through turbulent air. Collisions can create mixed shapes and small clusters, because when two crystals hit each other, they might stick together, especially if there's any liquid, water on their surfaces, or if they hit with the right geometry to create contact along multiple points, and the resulting cluster might look like two distinct crystals joined side by side. Or the collision might be violent enough to break both crystals and create something entirely new from the fragments. And over the course of a snowfall, billions of such collisions are happening. Billions of interactions between falling crystals, and some percentage of these interactions create the clusters and aggregates that contribute to the variety of forms reaching the ground. The air a snowflake travels through is layered, and those layers can affect how it grows, because the atmosphere isn't uniform but rather stratified, with different temperatures at different altitudes, different humidity levels, different wind speeds, and a falling snowflake moves through these layers like moving through different rooms in a house. And just as each room in a house might have different lighting, different temperature, different ambience, each layer of the atmosphere has its own character, its own influence on crystal growth, and the snowflake responds to each layer, adjusts its growth, changes its form, and the final crystal that lands on the ground is the sum of all these influences, the accumulated result of passing through all those atmospheric rooms. A snowflake's final shape is like a quiet summary of its path, a frozen record of everywhere it's been, every condition it experienced, every layer of air it passed through, And while we can't read this record in precise detail, can't reconstruct the exact trajectory and history from the crystal's shape alone, we can appreciate that the shape contains information, contains memory in a sense. And this idea of form as memory is philosophically rich suggests that everything carries within it the traces of its history, that you can't fully understand a thing without understanding how it came to be, and the same is true for you. Your current state contains the accumulated influence of everything you've experienced, every condition you've passed through, and understanding this can help you be more patient with yourself, more accepting of where you are right now. Even imperfect flakes can be beautiful because they show motion and history, because perfection is static, but imperfection suggests process, suggests that something happened, that change occurred, that the object before you has a story rather than being a timeless ideal form. And when you look at an irregular snowflake, a broken one, a simple one without much elaboration, you can imagine the path it took, the wind that might have broken it, the dry air that might have limited its growth, the warm layer it might have briefly passed through, and this imaginative engagement with the object makes it more interesting than perfect symmetry might be, makes it more human in a way, more relatable, because we too are imperfect, we too carry the marks of our journey. In a gentle way, snowflakes remind us that process matters more than perfection, that the journey shapes the destination, that how something comes to be is as important as what it becomes, and this is worth remembering as you move towards sleep, because sleep isn't about forcing yourself into a perfect state of unconsciousness, but rather about allowing the natural process of falling asleep to unfold, about trusting the journey even if it takes longer than you'd like, about accepting that some nights sleep comes easily, and other nights it requires more patience, and both kinds of nights are valid. Both are part of the human experience, and neither represents failure or success, but simply the natural variation in how our bodies and minds work. A crystal is a solid with atoms or molecules arranged in a repeating structure, and this definition applies to ice as much as it applies to diamond or quartz or salt, because all these materials share that fundamental property of ordered repetition of atoms or molecules locked into regular geometric patterns that extend in 3 dimensions, creating solids that have characteristic shapes and properties determined by their internal structure. And understanding this helps us see snowflakes not as unique exceptions, but as members of a larger family, as examples of a common phenomenon in nature, as particular expressions of the general tendency of matter to organize itself into ordered patterns when conditions allow. Ice is a crystal because its water molecules form an ordered pattern, that hexagonal lattice we discussed earlier. And when you hold an ice cube, you're holding a crystal just as surely as when you hold a quartz crystal, or a diamond, the difference being mainly in the size and perfection of the crystal structure, and in the fact that ice melts at a much lower temperature than most other crystals you might encounter. But the fundamental nature is the same, order at the molecular level expressing itself as structure at the macroscopic level, and this connection between the very small and the large enough to see is one of the most fascinating aspects of studying crystals, the way microscopic arrangements determine visible properties. Many minerals also form crystals, each with its own geometric tendencies, because the same principles that govern ice formation govern the formation of rock crystals, the way that atoms arrange themselves into repeating patterns, the way that internal structure determines external form, and you can see this in the regularity of mineral crystals, the way quartz tends to form hexagonal columns, the way halite forms cubes, the way calcite forms rhombohedra, each mineral expressing its particular atomic geometry in its visible shape. And this universality of crystalline form across different materials suggests deep truths about how matter organizes, about the mathematical nature of physical reality. Salt crystals often form cubes, showing their own repeating order, and you can observe this yourself if you dissolve salt in water and then let the water evaporate, watching as tiny cubic crystals appear and grow, each one a miniature expression of the cubic arrangement of sodium and chloride ions in the salt crystal lattice. And these cubes are different from ice's hexagons or expressing different symmetry, but the underlying principle is the same: atoms or molecules or ions finding their preferred arrangement and repeating that arrangement over and over, creating order from the tendency of matter to minimize energy and maximize stability. Quartz crystals form in ways that reflect their internal structure, often growing as hexagonal prisms terminated by pyramidal faces, and these natural quartz crystals can be quite large, can be beautiful specimens that people collect and display, and the same substance, silicon dioxide, that forms these large crystals also exists in other forms, in sand grains and glass, in many rocks, but only when conditions allow the slow-ordered growth of a crystal. Do you get that characteristic hexagonal shape? And this again reminds us that form depends on process, that the same material can produce very different results depending on how it's allowed to organize. Snowflakes are special because they form in the air and fall to us as tiny finished sculptures, and unlike most crystals that grow attached to surfaces that form in solid rock or in solutions, snowflakes grow while freely falling through the air, growing while moving, building themselves in three-dimensional space without any substrate to support them except the air itself. And this free-floating growth is part of what allows snowflakes to develop such delicate structures, such extended arms and branches that would be difficult to maintain if the crystal were growing while attached to a surface and subject to gravity pulling it down, and the fact that they fall to us, that we can catch them and observe them, makes them accessible in a way that crystals hidden in rock or growing in caves are not. Crystal growth is shaped by both internal structure and external conditions, and this interplay between the internal and external, between what the material wants to be based on its atomic structure and what the environment allows it to become based on temperature and available building materials and time, this interplay creates the diversity of crystal forms we observe in nature, and the same interplay exists in your own life, between your internal tendencies, your personality, your desires, your natural inclinations, and the external conditions you find yourself in, the opportunities available, the constraints you face, the resources you can access, and the life you live is the result of this interplay, is shaped by both what you bring and what the world offers. In snowflakes, the external conditions are the temperature and moisture of the cloud, as we've discussed extensively, and these conditions change from moment to moment as the snowflake falls, creating a varying environment that influences growth, and the snowflake has no control over these conditions, can only respond to what it encounters, and yet from this passive response emerges active structure, emerges beauty and complexity, emerges form that seems almost intentional, even though it arises entirely from simple physical processes, and perhaps there's wisdom in this passivity, in this willingness to respond to conditions rather than trying to control them, in this acceptance that beauty can emerge from allowing rather than forcing. That combination creates the enormous variety we see, because neither internal structure alone nor external conditions alone would be sufficient to produce the diversity of snowflake forms. The internal structure provides the hexagonal foundation, but the external conditions determine how that foundation is elaborated, how tall the crystal grows, how branched, how ornate, and the interaction between these two factors, one fixed and one variable, creates what mathematicians might call a parameter space with rich structure, a space of possibilities that nature explores thoroughly over the course of billions of snowfalls, creating examples of forms we can observe and appreciate. Nature often builds beauty by repeating simple rules in slightly different conditions, and this principle extends far beyond snowflakes, appears in the branching of trees and rivers, in the spiral patterns of galaxies and hurricanes, in the distribution of leaves on a stem and the arrangement of seeds in a sunflower. And what all these examples share is the combination of simple underlying rules, geometric or mathematical principles that govern how things grow or flow or organize, with variations in local conditions that ensure no two examples are exactly alike. And this combination of order and variation creates patterns that humans find aesthetically pleasing, that we recognize as beautiful, that draw our attention and our appreciation. Snowfall often feels calming because it changes the sound of the environment, as we've touched on before, but it's worth emphasizing this acoustic quality again because it's such a large part of why snow creates the feeling it does, why a snowy day or night feels different from a rainy day or clear day, and the sound dampening happens because snow absorbs sound rather than reflecting it, because the complex surface of accumulated snow crystals captures sound waves and converts their energy to heat through friction and absorption rather than bouncing them back into the environment. And this creates a quieter world, a world where sounds don't travel as far, where the ambient noise level drops, where silence becomes more noticeable. Fresh snow can muffle echoes and soften distant noises, turning a normally noisy environment into something more intimate, more contained. And if you've ever been in a city during a heavy snowfall, you know how different it sounds, how the usual urban roar becomes muted, how you can hear your own footsteps more clearly because there's less background noise competing for your attention, how conversations seem to stay local rather than carrying across distance, and this acoustic transformation contributes to the sense that snow creates a different world, a quieter world, a world more suitable for reflection and rest. Snow also changes how light behaves, making scenes feel brighter and smoother, because as we discussed, the snow reflects light diffusely, scattering it in all directions rather than creating the directional reflections you get from water or glass. And this diffuse reflection means that shadows are softer, that light wraps around objects more, that the overall illumination is more even. And photographers know this quality, know that overcast days with snow on the ground create a particular kind of light that's very flattering, very soft, very different from the harsh shadows and bright highlights you might get on a sunny summer day. Clouds that bring snow can create even lighting, reducing harsh shadows, because snow clouds tend to be thick and low, creating an overcast sky that diffuses sunlight, that spreads it out across the cloud layer rather than letting it through in direct beams. And this diffused light combined with the reflected light from snow on the ground creates illumination that comes from all directions, that wraps around objects, that minimizes contrast. And this even lighting is part of why snowy landscapes often look so peaceful, so calm, so gentle, because the visual environment lacks the drama of strong light and deep shadow, instead offering a more uniform, more soothing visual field. The slow drifting motion of flakes can be naturally relaxing to watch, because the movement is steady but not rushed, purposeful but not urgent, and when you watch snow falling you can let your eyes track individual flakes, can follow their meandering descent, can appreciate the slight variations in their speed and trajectory. And this kind of visual tracking can be meditative, can quiet your thoughts the way watching flames in a fireplace can quiet your thoughts, by giving your attention something gentle to focus on, something that moves but doesn't demand interpretation or response, something you can simply observe without needing to do anything about it. People often describe snowfall as quiet because it encourages stillness, both because of its acoustic properties and because something about the experience of watching snowfall makes you want to be still yourself, to stand at the window or sit on the porch and just watch, to let the world slow down around you. And this encouragement towards stillness is valuable in a culture that often pushes toward constant activity, constant productivity, constant motion, and snow offers permission to pause, to rest, to simply be present without doing. And you can accept that same permission now, can let yourself be still, can release any pressure to be active or productive and simply allow yourself to rest. Snow can make outdoor colours look simpler, reducing the visual complexity of the environment to a limited palette of whites and greys and gentle blues. And this simplification can be restful for the eyes, can reduce visual clutter, can create a sense of cleanness and clarity. And many people find monochromatic or limited palette scenes naturally calming, find that when the visual field is less busy, their mind feels less busy too, and a snow-covered landscape offers this kind of visual simplicity, this reduction of the world to essential forms and a narrow range of tones, and you can bring this same simplification to your thoughts now, can let go of mental clutter, can allow your inner landscape to become as simple and clean as a field of fresh snow. Indoors, the idea of snow can feel cozy, creating that classic contrast between the warm room and the cold world outside, between the soft light of a lamp and the blue-white glow of snow through the window, and this contrast is part of what makes winter evenings feel so comforting. The sense of being safe and warm while outside nature is expressing its power through cold and snow, and the boundary between inside and outside becomes meaningful, becomes a source of comfort rather than just a physical fact. And you might feel this coziness now, lying in your bed, warm and comfortable, while the night continues outside, protected and safe, able to rest while the world takes care of itself without your intervention. The contrast can make blankets and soft light feel even more comforting, because comfort is often experienced most acutely when it contrasts with discomfort, when warmth feels warmest because cold exists nearby, when softness feels softest because hardness is possible, and the presence of snow outside amplifies the comfort of being inside, makes you appreciate the blankets and pillows and warm room more than you might on a mild night. And this appreciation, this gratitude for comfort, can help you settle more deeply into rest, can help you feel the full pleasure of being exactly where you are right now. Snowflakes can be a reminder that small things can change the feeling of a whole world, because each individual snowflake is tiny, weighs almost nothing, has virtually no impact by itself, and yet when millions of snowflakes accumulate, the whole landscape transforms, the whole atmosphere changes, the whole feeling of being outside shifts from one state to another, and this reminds us that large changes can come from small increments, that transformation doesn't require dramatic single events, but can emerge from the accumulation of small changes over time, and this principle applies to many areas of life, to how habits form, to how skills develop, to how relationships deepen, all through small repeated actions that accumulate into something substantial. Snow on the ground can change shape as crystals settle and press together. Because snow is not static after it lands, it continues to evolve, continues to respond to conditions, and the weight of new snow falling on top of old snow compresses the lower layers, forces air out from between crystals, makes the snow denser and more compact, and wind can move snow around, can create drifts in some areas while clearing other areas down to bare ground, and temperature changes can cause melting and refreezing, can transform the crystal structure, and all these processes mean that the snow you see today will look different tomorrow, will have changed even if no new snow has fallen. Over time, sharp crystal edges can round off, because molecular scale processes continue even in solid ice, with water molecules occasionally moving from one position to another, and sharp points and thin edges are less stable than rounded forms, have higher energy, and so over time the sharp features tend to soften, tend to become more rounded, and this is particularly noticeable when snow goes through cycles of slight melting and refreezing, when liquid water can flow and redistribute before freezing again, smoothing out the finest details, removing the delicate branches and leaving more compact forms, and old snow that has been on the ground for weeks often looks very different from fresh snow, has lost that fluffy quality, and become more granular, more compact, more like ice. Snow can become denser as air pockets shrink, both from compression under the weight of additional snow and from the settling that happens as crystals shift and rearrange, as they find more stable positions, as gravity slowly pulls everything downward and eliminates empty spaces. And this densification is why snow depth decreases over time even without melting, why a foot of fresh snow might settle down to 8 or 9 inches after a few days, and very old snow that has been on the ground for months in cold climates, can become so dense and hard that it's difficult to distinguish from ice. And eventually this is how glaciers form, from snow that accumulates year after year and compresses under its own weight until it transforms into glacial ice. Sunlight can cause melting and refreezing, changing the snow's texture, especially when you have warm sunny days followed by cold nights, which creates cycles where the surface of the snow melts during the day and then refreezes at night, and these cycles create a crust on top of the snow, a harder layer that can support your weight. And this crusty snow has a very different quality from fresh powder. It crunches differently when you walk on it. It reflects light differently. It feels different if you touch it, and these transformations show how responsive snow is to its environment, how it continues to change and adapt based on weather conditions. Wind can sculpt snow into drifts and ripples, creating patterns that look almost like sand dunes, because snow when it's dry enough can be moved by wind much, like sand can, and strong winds can create beautiful sculptural forms in snow, sweeping it into curved shapes, creating sharp ridges, forming overhanging cornices on the lee side of obstacles, and these wind-created patterns add another dimension to snow's aesthetic appeal, create shapes that seem almost artistic in their curves and contours, and if you've seen these patterns, you know how striking they can be, how they can make a snowy landscape look like something from another world. Snow layers can form with different textures depending on weather changes, and if you dig down into deep snow you can often see these layers, can see where one snowfall ended and another began, can see how the crystal structure differs between layers. And scientists who study snow, particularly those interested in avalanche forecasting, pay close attention to these layers because weak layers can create avalanche hazards. But for our purposes, we can simply appreciate that snow has this layered structure. This history written in strata like the layers in sedimentary rock, each layer representing a different time, a different set of conditions. These layers can tell a quiet story of different storms and temperatures, and someone trained to read them can look at a snow pit, can examine the layers, and reconstruct the weather history of the winter. Can say this layer fell during a cold dry period, this layer during a warmer wet period, this layer was affected by wind, This layer experienced extensive melting and refreezing, and the snow becomes an archive, becomes a record of what has happened. And this record-keeping function of snow is another example of how nature preserves information, how the present contains traces of the past if you know how to look for them. Snow can insulate soil and help protect small plants and animals from extreme cold, and we mentioned this before, but it's worth emphasizing because it's such an important ecological function. The way snow creates a protected space underneath itself where temperatures remain relatively stable even as air temperatures fluctuate, and small mammals can tunnel through this space, can move around and forage even in the middle of winter, protected from both the cold and from predators. And this subnivean zone, as scientists call it, is an entire hidden world that exists beneath the snow, a world that most people never think about, but that's crucial for many species. Snowmelt later helps feed streams and rivers, connecting snowfall to the wider water cycle, because snow is stored water, frozen precipitation that will eventually melt and flow, and in many regions the spring snowmelt is the most important source of water for rivers and reservoirs, more important than direct rainfall, and the timing of snowmelt affects everything from agriculture to hydroelectric power generation to fish spawning cycles. And so snow is not just beautiful and peaceful, it's also functionally important. It's a crucial component of Earth's water distribution system, and this functional importance exists alongside its aesthetic appeal, the same thing serving both practical and emotional needs. Even as snow changes, it keeps its gentle role, softening the world and slowing things down, because whether it's fresh powder or old corn snow or a frozen crust, it still creates that distinctive snowy atmosphere, still transforms the landscape, still affects how light and sound behave, still invites a more contemplative pace. And this persistence of character through transformation is another lesson snow offers. The idea that you can change in your details while maintaining your essential nature, can adapt to conditions while staying true to what you fundamentally are. Snowflakes begin from something almost invisible, from water vapor that's dispersed through cold air, from moisture so diffuse that you can't see it, can't feel it, can barely detect its presence except through its effects, and yet from this, near nothingness emerges the snowflake, emerges structure and form and visible beauty. And this emergence is happening constantly in the atmosphere, this transformation of the invisible into the visible, of the formless into the formed. And you participate in similar transformations every day, taking abstract thoughts and making them into words, taking desires and making them into actions, taking what's invisible inside you and bringing it out into the visible world. They grow one molecule at a time, patiently and quietly, without rush, without anxiety about completion, without comparing their progress to other snowflakes. They simply grow at the rate that conditions allow, adding molecule after molecule in a process that is both mechanical and beautiful, both determined by physics and aesthetically pleasing to human observers. And this patient growth is something you can emulate as you drift towards sleep, not forcing the process, not rushing it, simply allowing it to unfold one moment at a time, one breath at a time, trusting that the accumulation of these moments will eventually carry you into rest. Their six-sided symmetry comes from the natural structure of ice, from the hexagonal arrangement of water molecules in the crystal lattice, and we've explored this idea from several angles now, have returned to it again and again because it's so fundamental to understanding snowflakes. And this kind of return, this circling back to key ideas, is how deep understanding develops, not through a single exposure but through repeated engagement, each time adding a bit more context, a bit more nuance, a bit more connection to other ideas. And the hexagonal structure is worth this repeated attention because it demonstrates so clearly how large-scale patterns emerge from small-scale rules. Tiny changes in temperature and humidity can shape each flake in a unique way, can create the variation we observe, can ensure that even flakes forming in the same cloud at the same time end up looking different from each other. And this sensitivity to conditions, this responsiveness to the environment, is characteristic of complex systems, of systems where small differences can be amplified into large differences through feedback and iteration. And you're also a complex system, also sensitive to conditions, also shaped by your environment in ways both large and small. And understanding this can help you be more compassionate with yourself, more aware that your state depends partly on factors outside your direct control. Many flakes are imperfect, and that imperfection is part of their story, part of what makes them interesting, part of what gives them character, And a snowflake with one broken arm or a symmetric development or irregular structure is not a failed snowflake. It's simply a snowflake that experienced particular conditions, that went through particular events during its formation. And in the same way, your own imperfections are not failures, but rather evidence of your journey, marks of what you've experienced, signs that you're a real person living in a real world rather than an abstract ideal existing in theoretical perfection. Snow on the ground feels calm because it scatters light and softens sound, and we've discussed both these properties multiple times now, have explored them from different angles, and this repetition is intentional, is designed to help these ideas settle into your awareness, to help you really feel the calmness that snow creates, to help you bring that quality into your own experience right now, because understanding how snow creates calm can help you access that calm yourself, can help you imagine it so vividly that your body responds as if it were real. Watching snow fall can slow the mind, like counting gentle breaths, because both activities give attention something rhythmic and peaceful to focus on, something that moves but doesn't demand analysis, something you can observe without needing to control or change, and this kind of witnessing, this pure observation without agenda, is naturally meditative, naturally quieting, and you can practice it now with your own breathing, can simply observe each breath without trying to change it, noticing the slight variations in depth and duration, the natural pauses between breaths, the way your body breathes itself without your conscious direction. The world doesn't rush snowflakes. They arrive on their own schedule, falling at the speed that gravity and air resistance determine, landing when and where they land without pressure to hurry, without judgment about whether they're fast enough or efficient enough. They simply are, simply exist, simply complete their journey in the time it takes, and you can adopt this same patience with yourself, can release any pressure to fall asleep quickly, can accept that sleep will come when it comes, that your only job is to create conditions that support rest and then allow the natural process to unfold. Tonight, you can let your thoughts fall the same way, softly, without effort, not trying to suppress them or control them, but simply allowing them to drift through your awareness, like snowflakes drifting through air, coming and going on their own schedule, settling where they settle, and as thoughts arise you can observe them without engaging, can let them pass through like clouds passing through the sky, not resisting them but also not following them, maintaining a gentle awareness that watches but doesn't grasp. And like fresh snow smoothing a landscape, sleep can smooth your mind into quiet rest, can cover over the roughness of the day's concerns, can create a blanket of unconsciousness that lets your nervous system recover, that gives your body time to repair and restore itself, that allows your mind to process and integrate the experiences you've accumulated. And this smoothing happens naturally when you stop resisting it, when you let go of the need to be awake, when you trust that sleep is safe and beneficial and that you can surrender to it completely. Take a slow inhale, drawing breath deep into your lungs, filling yourself with air like a snowflake collecting water vapor, and then a longer exhale, releasing that breath slowly and completely, letting it carry away any tension or worry or mental noise, and imagine soft snowfall settling over everything, covering your body in gentle white crystals, each one tiny and perfect in its imperfection, each one contributing to a growing blanket of peace. And the snowflakes keep falling, keep accumulating, keep building a layer of quiet rest that grows thicker and deeper with each passing moment. The snowflakes land on your forehead, cooling any tension there, smoothing away any tightness, and they land on your closed eyes, gentle and soft, bringing a feeling of deep relaxation to the muscles around your eyes, and they land on your cheeks and jaw, encouraging those muscles to soften and release, and your whole face becomes peaceful under this accumulation of gentle snow, becomes smooth and relaxed, and the snow continues falling, landing on your neck and shoulders, on your chest and arms, on your belly and legs, and everywhere the snow touches. Tension melts away, replaced by soft white peace. The snow accumulates around you, covers the bed, fills the room with gentle white light, and you sink deeper into this snowbank of rest. Feel yourself cradled by soft coolness, supported by accumulating peace, and your breathing continues slow and steady. Like the fall of individual snowflakes, each breath adding to the growing quiet, each exhalation releasing you further into rest, and you don't need to do anything now except allow this process to continue, allow the snow to keep falling, allow yourself to keep settling, allow sleep to arrive in its own time like snow arriving from cold clouds. The six-pointed structure of ice, the hexagonal lattice of water molecules, creates a foundation of order, and on that foundation infinite variation can build, infinite unique expressions of the same fundamental pattern. And you too have a foundation, a basic structure of who you are, and on that foundation your life builds infinite variations, infinite unique moments that are yours alone, and tonight that foundation supports you, holds you, allows you to rest completely, allows you to trust that you are safe and stable and able to sleep. Snow crystals forming in clouds right now, even as you drift towards sleep, adding molecule after molecule in patient accumulation, building structure from vapor, creating beauty from simple rules, and you are also building, also accumulating, also creating. But right now you can stop building and simply rest, can trust that tomorrow will bring new opportunities for growth, new conditions for creation, and tonight is for settling, for allowing, for soft white peace. The sound dampening quality of snow, the way it absorbs noise and creates quiet, extends into your mind now, absorbing the noise of thought, creating mental quiet, and any sounds you hear become muffled and distant, become part of the peaceful atmosphere rather than disruptions to it, and you sink deeper into this quiet. Feel it wrapping around you like snow wrapping around a sleeping landscape, protective and gentle and complete. Fresh snow is mostly air, tiny pockets trapped between ice crystals, and your mind is becoming like this too, mostly space, mostly emptiness, with thoughts scattered like crystals, but the dominant quality being spaciousness, openness, room to breathe and be. And this spaciousness feels good, feels natural, feels like coming home after a long journey, and you settle into it gratefully, thankfully, peacefully. The slow drift of falling snow, moving with air currents, rising and falling in gentle eddies before finally settling to earth, and your consciousness is like this now, drifting without direction, moving with the currents of nearly sleep, and eventually you will settle, will land, will transition from this gentle drift into actual sleep, and when that happens you won't notice, won't mark the moment, will simply find yourself on the other side, having crossed the boundary without awareness, and that's perfect. That's exactly how it should be. Snowflakes as little weather notes, tiny records of atmospheric conditions, and your dreams tonight might be little notes too, little records of your day, your concerns, your experiences transformed and recombined into new patterns, into strange and beautiful combinations. And these dream notes serve a purpose, help your mind process and integrate, help you make sense of what you've lived, and you can trust this process, can trust that your sleeping mind knows what it's doing, knows what you need. The brightness of snow, reflecting available light, making night seem less dark, and there's a brightness in you too, a light that persists even in dark times, even when you feel lost or confused, and this inner light doesn't require your conscious effort to maintain, it simply is, simply exists as part of your fundamental nature, and you can rest. Knowing this light continues whether you're awake or asleep, whether you're aware of it or not. The transformation of familiar places by snow, making known landscapes seem new and strange and beautiful, and sleep does this too, transforms the familiar landscape of your daily concerns, makes them seem different when you wake, gives you fresh perspective, renews your ability to engage with challenges, and so going to sleep is not escape but transformation, not running away but changing the angle of view, and this transformation is valuable, is necessary, is part of how you maintain resilience and creativity. Crystal growth shaped by internal structure and external conditions, and you are shaped the same way, by who you are inside and by what the world offers outside, and both factors matter, both contribute, and you don't need to fight either one but can work with both, can honour your internal nature while adapting to external conditions, can be both true to yourself and responsive to reality. And this balance is something you maintain not through rigid control, but through flexible awareness, through constant small adjustments like a snowflake responding to slight changes in the air around it. The enormous variety of snowflake forms, the countless different ways that hexagonal ice crystal structure can be elaborated, and this variety mirrors the variety of human experience, the countless different ways that basic human nature can be expressed, and your particular expression of humanity is unique, is valuable, is worth honouring, and part of honouring it is allowing yourself to rest when you need rest, allowing yourself to stop and sleep and trust that you'll wake restored. Temperature and humidity shaping snowflake growth, determining whether crystals become plates or columns or dendrites, and your sleep is shaped by conditions too, by how comfortable you are physically, by how settled you are mentally, by how safe you feel emotionally, and you've done what you can to optimize these conditions, have made your space as comfortable as possible, and now you can stop trying to control outcomes and simply accept what emerges, accept whatever kind of sleep comes tonight, knowing that any sleep is valuable, any rest is beneficial. Snowflakes in clouds, spending time growing before falling to earth, and you've spent your time today growing too, learning, experiencing, engaging with your life. And now it's time to fall, to descend into rest, to complete the cycle that allows for new growth tomorrow. And this falling is not failure but fulfillment, not giving up but arriving at the natural conclusion of the wake cycle, and you fall gratefully, peacefully, without resistance. The quiet insistence of six-sided symmetry, appearing again and again in snow crystals of all types, and there are patterns. In your life too, themes that recur, lessons that present themselves repeatedly in different forms, and rather than fighting these patterns, you can accept them, can work with them, can recognize that some aspects of your nature are fundamental and will keep expressing themselves no matter how conditions change, and this recognition can bring peace, can help you stop struggling against yourself and instead align with who you actually are. Snow continuing to change after landing, settling and compacting and transforming, and you will continue to change too. Tonight's sleep is not an endpoint but a transition. You will wake changed, will be slightly different tomorrow than you are today, and this constant transformation is life itself, is growth and adaptation, and the unfolding of your particular journey through time, and you can embrace this changeability, can see it as opportunity rather than threat, can trust the process of becoming. Old snow becoming dense and hard, eventually transforming into something almost like ice, and your experiences too accumulate and compress and transform into something solid, into wisdom, into character, into the foundation of who you are, and tonight's rest contributes to this process, allows the day's experiences to compress and integrate, allows what was loose and scattered to become more solid and usable, and you can trust this transformation, can trust that your sleeping mind will do its work. Wind sculpting snow into beautiful patterns, into drifts and ripples and curves, and the forces that move through your life sculpt you too, shape you into patterns that are uniquely yours, that reflect your particular combination of circumstances and responses, and these patterns are beautiful even when you can't see them yourself, even when you focus on flaws rather than overall form. And tonight as you sleep, these forces continue their gentle sculpting, continue shaping you into who you're becoming. The layered structure of accumulated snow, each layer representing different conditions, different times, and your personality is layered too, built up over years, each experience adding another thin layer to the whole, and all these layers together make you who you are, and you don't need to understand every layer, don't need to analyze your entire history, can simply accept yourself as the accumulated result of all you've lived, and this acceptance brings peace, brings rest. Snow insulating the ground, protecting what lies beneath, and sleep insulates you too, protects you from the constant demands of consciousness, gives you time in a protected space where you don't need to respond or perform or achieve, where you can simply be without agenda, and this protected space is valuable, is necessary, is something to be grateful for. Snowmelt feeding streams and rivers, connecting the winter's snow to the spring's growth, and your rest tonight connects to tomorrow's activity, feeds your energy and creativity, makes possible whatever you'll do when you wake, and this connection means rest is not passive but productive, not empty but full of potential, not wasting time but investing it. The gentle roll of snow, softening and slowing, persisting through all its transformations, and the gentle roll of sleep is similar, softening your edges, slowing your racing thoughts, persisting as a fundamental need regardless of how busy your life becomes, and you honor this need now, accept it, allow it to fulfill its gentle role in your life. Snowflakes beginning from invisible vapor, growing patiently molecule by molecule, expressing hexagonal symmetry, responding to tiny environmental changes, developing unique forms through the interaction of simple rules and varying conditions, eventually falling to Earth to accumulate and transform and fulfill their role in the larger system. and you began from invisible potential to have grown patiently through years, express your own fundamental nature while, responding to circumstances, have developed into a unique individual through the interaction of who you are and what you've experienced. And now you settle into rest to fulfill your need for sleep, to complete this cycle so tomorrow's cycle can begin. The breath continues, slow and steady, in and out like snow falling and settling, and with each exhalation you release a bit more, let go a bit further, sink a bit deeper into the soft accumulation of peace that surrounds you, supports you, holds you safe, and the snow keeps falling in your imagination, keeps building depth and quiet, keeps creating this peaceful landscape where you can finally, fully, completely rest, where sleep is not something you have to chase or achieve, but something that arrives naturally, inevitably, like snow falling from cold clouds, and you are ready, you are peaceful, you are drifting now into that soft white quiet where thoughts fade and consciousness dissolves and sleep finally, gently, peacefully arrives. The next story is about to begin, please relax and enjoy. A rainbow is an arc of coloured light that appears in the sky under certain conditions. It's one of those sights that can make you pause, even on a busy day, and simply look up. But what makes it happen? What turns ordinary sunlight and water droplets into bands of soft colour stretching across the sky? Tonight, as you settle in, we're going to explore rainbows in a gentle, thorough way, understanding the science behind them, the geometry that shapes them, and the quiet reasons they appear and fade. There's no rush. We'll take our time with each idea, letting it unfold slowly, the way a rainbow itself unfolds across the sky after a storm passes. Rainbows happen when sunlight interacts with water droplets in the air. That simple sentence holds the entire process, but we can unpack it carefully, step by step, until the mechanism becomes clear and familiar. Imagine sunlight, bright, white, seemingly uniform, streaming through the atmosphere. Looks like one pure beam of light, but actually it's carrying many different wavelengths bundled together. Our eyes interpret these wavelengths as different colours. When this bundle of light meets a water droplet hanging in the air, something wonderful and precise happens. The droplet acts like a tiny lens and mirror at the same time, bending the light, bouncing it around inside and sending it back out in a new direction. And in that process, the white light gets spread apart into its component colours, creating the spectrum we recognise as a rainbow. To understand this properly, we need to think about three main processes: refraction, reflection, and dispersion. These are the quiet workers behind the rainbow, and each one plays a specific role. Let's start with refraction. Refraction is the bending of light as it moves from one material to another. Light travels at different speeds depending on what it's moving through. In the vacuum of space, light moves at its absolute fastest, about 300 million meters per second. But when light enters a denser medium, like air or water, it slows down slightly. And when light changes speed at an angle, it bends. This bending is refraction. If you've ever looked at a straw in a glass of water and noticed that it seems to break or shift at the surface, you've seen refraction at work. The light reflecting off the straw bends as it moves from water into air, and your brain interprets that bent light as a straw that looks offset from where it actually is. Reflection is simpler to picture. Reflection is light bouncing off a surface. When you look in a mirror, you're seeing reflected light. The mirror's smooth surface sends light back toward you at predictable angles. Inside a raindrop, light can reflect off the inner surface of the droplet, bouncing back instead of passing straight through. That internal reflection is a key part of forming a rainbow, because it sends the light back toward the direction it came from, back toward the observer, back toward you. Dispersion is the third process, and it's the one that creates the colours. Dispersion is the spreading of white light into different colours, and it happens because different wavelengths of light bend by slightly different amounts when they refract. White sunlight isn't really white in a pure sense. It's a mixture of many wavelengths, each corresponding to a different colour. Red light has a longer wavelength, while violet light has a shorter one. When this mixture enters a water droplet and slows down, the different wavelengths slow down by slightly different amounts, and that causes them to bend at slightly different angles. Red bends a little less than orange, orange bends a little less than yellow, and so on, all the way to violet, which bends the most. This spreading apart of colours is dispersion, and it's what turns a single beam of white sunlight into a fan of colours inside the droplet. So here's the sequence, in slow motion. A beam of sunlight approaches a raindrop hanging in the air. The sunlight is white, a mixture of all colours. As it enters the droplet, it crosses from air into water, and because water is denser, the light slows down and bends. That's refraction. But the bending isn't uniform. The white light spreads into its component colours as it refracts, with violet bending the most and red bending the least. Now the light is inside the droplet, fanned out into a spectrum. Some of this light continues through and exits the other side, but some of it hits the inner back surface of the droplet and reflects, bouncing back toward the front. Then, as this reflected light exits the droplet, it refracts again, bending once more as it moves from water back into air. This second refraction spreads the colours even further. The result is that the light leaving the droplet is separated into distinct colours, each travelling in a slightly different direction. Rainbows are not physical objects you could touch. They're a view of light at certain angles. This is important to understand, and it can feel a little strange at first. A rainbow doesn't exist in one specific place in the sky. It's not hanging there like a banner or an arch made of mist. Instead, a rainbow is an optical phenomenon, a pattern of light that you see when you're in the right position, when countless droplets are scattering light toward your eyes at just the right angles. If you move, the rainbow seems to move with you, because the droplets sending light toward your new position are different droplets. The rainbow you see is built from the light reaching you, and someone standing even a few meters away is seeing light from a different set of droplets. You're each seeing your own rainbow, even though they look similar. A calm way to picture a rainbow is as light taking a gentle detour through tiny drops. Instead of continuing straight from the sun to your eyes, the light takes a winding path, into a droplet, bouncing around inside, bending twice, and then arriving at your eyes with its colours spread apart. That detour, that brief journey through water, is what creates the arc of colour. And because there are millions of droplets in the air during and after a rainstorm, millions of these detours are happening at once, each one contributing a small piece of the rainbow you see. Now that the idea is settled, we can drift closer to a single raindrop and watch how it quietly turns sunlight into colour. Imagine one droplet hanging in the air. It's small, maybe a millimetre or two across, roughly spherical, held together by surface tension. Sunlight approaches from one direction and the droplet is about to do its work. When sunlight enters the raindrop, it slows down slightly and bends. The light was moving at full speed through the air and now it crosses into water, which is denser. The speed change happens right at the boundary, and because the light is entering at an angle, not head-on, it bends. This is refraction in action, the same process that makes objects underwater look shifted. Different colours bend by slightly different amounts. This is because different wavelengths interact differently with water. The speed at which light travels through a material depends on the wavelength. Shorter wavelengths, like violet and blue, slow down more in water than longer wavelengths, like red and orange. And when light slows down at an angle, the amount it bends depends on how much it slows. So violet light, slowing down the most, bends the most. Red light, slowing down the least, bends the least. The result is that as the white sunlight enters the droplet, it fans out into a spectrum, with the colours spreading apart. After bending in, some of the light reflects off the inside back surface of the droplet. Not all of the light does this. Some passes through and exits the droplet from the backside, heading away from the observer. But a significant portion hits the curved inner surface at just the right angle and bounces back like a ball bouncing off a wall. This internal reflection is crucial. It redirects the light back toward the front of the droplet, back toward the direction it came from, back toward the observer. Then the light bends again as it exits the droplet. It crosses from water back into air, speeding up again, and because it's crossing at an angle, it bends once more. And just like the first refraction, this second bending is different for different colours. The violet light, which bent the most going in, bends the most going out. The red light, which bent the least going in, bends the least going out. So the colours spread even further apart as they exit. The exiting light spreads out with colours separated into a fan-like pattern. If you could somehow watch a single droplet doing this work, you'd see a cone of coloured light emerging from it, with red light heading in one direction, violet in another, and all the other colours in between. The droplet has taken white sunlight and turned it into a rainbow of separate beams, each one heading off at a slightly different angle. The strongest rainbow light leaves the droplet at a specific range of angles. This is where geometry comes in. Because of the way refraction and reflection work inside a sphere, the light doesn't spread out evenly in all directions. Instead, there's a particular angle where the light is concentrated, where the rainbow is brightest. For the main rainbow, the one most people see, the concentrated light exits at an angle of about 42 degrees from the direction opposite the sun. If you imagine a line going from the sun through your head and out the other side, that line points to a spot in the sky directly opposite the sun, and the rainbow appears in a circle around that spot, at a constant angle of about 42 degrees from it. Each droplet sends different colours toward different directions, and this is key to understanding why a rainbow has the shape it does. A droplet doesn't send all colours to one observer. Instead, it sends red light in one direction, orange in a slightly different direction, yellow in another, and so on. So when you look at a rainbow, the red light you're seeing is coming from one set of droplets, the orange from a slightly different set, the yellow from yet another set, and so on across the spectrum. Together, countless droplets create the smooth arc we see as one rainbow. Each droplet is contributing just one colour to your view, but because there are so many droplets, and because they are arranged in the sky at all the right angles, the combined effect is a continuous band of colour stretching across the sky. With that quiet droplet journey in mind, we can explore the simple geometry of why rainbows form arcs instead of straight lines. A rainbow's shape comes from angles, not from a fixed location in the sky. This is one of those ideas that can take a moment to settle in, but once it does, it explains so much about how rainbows behave. The rainbow isn't painted on the clouds, and it isn't hanging at a certain distance from you. Instead, it's defined by an angle, the angle between the direction of the sunlight and the direction of the light reaching your eyes after passing through the droplets. The centre of the rainbow is directly opposite the sun, along a line from your eyes. This point is called the antisolar point. If you draw an imaginary line from the sun straight through your head and continuing out the other side, that line points to the antisolar point. It's the exact opposite of the sun's position in the sky, and the rainbow appears at a constant angle around the antisolar point, about 42 degrees for the main rainbow. A constant angle around a point forms a circle. If you stand in one spot and mark every direction that's exactly 42 degrees away from a central point, you get a circle. The rainbow works the same way. Every droplet that's positioned at exactly 42 degrees from the antisolar point relative to your eyes can send its brightest light toward you, and because there are droplets all around you in the sky, wherever there's rain or mist, the ones that happen to be at that 42-degree angle form a circle. From the ground, we usually see only part of that circle, so it looks like an arc. Why? Because the ground blocks the lower half of the circle. The antisolar point is usually below the horizon when the sun is high, or just at the horizon when the sun is low. So the circle of droplets at the right angle is partly below the ground, where we can't see it. What we see is the upper portion of the circle, the arc. But the full geometric shape is a circle, and from higher viewpoints like airplanes, people can sometimes see more of the circle. Passengers on planes have reported seeing circular rainbows, or at least much more complete arcs, because from up high, the ground doesn't block as much of the lower portion. The higher the sun is in the sky, the lower the rainbow arc appears. This makes sense when you think about the antisolar point. If the sun is high, the antisolar point is low, and the circle around it is mostly below the horizon. You'll see just a small arc peeking above the ground. If the sun is low, the antisolar point is high, and more of the circle is above the horizon. The rainbow can rise higher in the sky. Rainbows often look best when the sun is low, such as in the morning or late afternoon. When the sun is near the horizon, the antisolar point is high, and the rainbow can form a tall, prominent arc. The light also has a warmer quality at sunrise and sunset, which can make the rainbow colours look richer. And because the sun is behind you and low, it's easier to have the right conditions: rain or mist in front of you, clear sky behind you, and good contrast between the bright rainbow and a darker background. Now we can gently name the colours and talk about their order, like reading soft bands on a quiet ribbon. The main rainbow usually shows red on the outer edge and violet on the inner edge. This order comes from how different wavelengths bend in water. Red light bends a little less than violet light, and because of this, red light exits the droplet at a slightly larger angle from the anti-solar point. That's why red appears higher and farther from the centre of the arc. Violet appears closer to the centre because it bends more, exiting at a smaller angle from the anti-solar point. The colours blend smoothly, rather than appearing as sharp stripes. In a prism, you might see fairly distinct bands of colour, but in a rainbow, the transition from red to orange to yellow, to green, to blue, to violet is gradual and soft. This happens because the droplets are different sizes, at different distances, and the light is blending together from countless sources. There's no hard boundary between where red ends and orange begins. Instead, one colour fades into the next in a continuous spectrum. Our eyes and brains help. Interpret these blends as a familiar spectrum. The human eye has 3 types of colour receptors: cones that are sensitive to red, green and blue wavelengths. Our perception of colour is constructed from the signals these cones send to the brain. So when we look at a rainbow, we're not seeing pure wavelengths in isolation, we're seeing a blend, and our brain is interpreting that blend as the familiar sequence of colours we've learned to recognise. Some people can see more distinct bands than others, depending on how sensitive their eyes are and how they've learned to categorise colours. The brightness of a rainbow depends on droplet size, sunlight intensity and background sky conditions. Larger raindrops, falling during a heavy shower, can create a brighter rainbow because they reflect and refract more light. Smaller droplets, like those in mist or light drizzle, create a paler, softer rainbow. The intensity of the sunlight matters too. If the sun is behind thin clouds, the rainbow will be fainter than if the sun is shining brightly through a clear patch of sky. And the background makes a big difference. A dark cloud behind a rainbow can make the colours appear more vivid by contrast. If the background sky is bright or hazy, the rainbow can be harder to see, the colours washed out by the surrounding light. With the main rainbow softly understood, we can drift into the lovely surprise of double rainbows, 2 arcs formed by a slightly different light path. A double rainbow happens when light reflects twice, inside raindrops instead of once. In the main rainbow, the light enters the droplet, reflects once off the back surface, and exits. But sometimes, instead of exiting after one reflection, the light reflects a second time before it leaves the droplet. This second reflection sends the light out at a different angle, creating a second rainbow. The second reflection causes the light to exit at a different angle. After the first reflection, the light is heading back, toward the front of the droplet. But if it hits the inner surface again before exiting, it reflects once more, bouncing back toward the rear. Then it exits, but now at a larger angle from the anti-solar point, about 50 to 53 degrees instead of 42 degrees, the secondary rainbow usually appears outside the main one. Because the light exits at a larger angle, the second rainbow forms a larger circle around the anti-solar point. If you're lucky enough to see a double rainbow, you'll notice the second arc is farther out, enclosing the first one. The colours in the secondary rainbow are reversed compared to the main rainbow. This is because of the second reflection. Each reflection flips the order of the colours. In the main rainbow, red is on the outside and violet on the inside. In the secondary rainbow, red is on the inside and violet on the outside. It's a mirror image, a reversed spectrum, and it's one of the easiest ways to tell the 2 rainbows apart. The secondary rainbow's often dimmer because extra reflections lose some light. Each time light reflects inside the droplet, some of it escapes instead of bouncing back. So the light that makes the second rainbow has gone through 2 reflections, and at each reflection a bit of intensity is lost. The result is a fainter arc, still beautiful, but softer and less vivid than the main rainbow. The region between the main and secondary rainbow can look darker. This darker band is sometimes called Alexander's band, named after Alexander of Aphrodisias, an ancient Greek philosopher who wrote about it. The reason for the darkness is that very little light exits the droplets at angles between the 2 rainbows. Almost all the light that leaves the droplets is concentrated at the 42-degree angle and the 53-degree angle. In between, there's a gap where few droplets send light toward you, and the sky looks darker by comparison. The double rainbow shows that small changes in light paths can create new patterns. One extra reflection inside a droplet and suddenly there's a second arc, reversed in colour, enclosing the first. It's like hearing a quieter echo of the same gentle song of light, a reminder that the same sunlight and the same water can create variations, each one following the same physical rules but producing a different visual effect. Now we can wander into the tiny details, why some rainbows look thicker or thinner, and how droplet size subtly changes the experience. The size of raindrops can affect how sharp the rainbow looks. Larger droplets can create brighter rainbows with more distinct colour bands. When droplets are big, they act like more effective prisms, bending and reflecting the light cleanly, and the result is a rainbow where the colours stand out, where the red and violet are clearly separated, and the arc has a crisp, defined appearance. Smaller droplets can create paler rainbows with softer edges, when droplets shrink down to the size of mist, or fog. Tiny spheres just a few micrometers across. The physics changes slightly. The light diffracts more, spreading out in different ways, and the colours overlap more than they separate. The result is a rainbow that looks washed out, sometimes almost white, with the colours so blended that they're hard to distinguish. Mist or fog can produce fogbows, which often look whitish and gentle. A fogbow is essentially a rainbow made by very small droplets. The droplets in fog are much smaller than raindrops, and at that size, diffraction, another light phenomenon, starts to dominate. Diffraction causes light to spread out and interfere with itself, and the result is that the colours don't separate as cleanly. Instead of seeing red, orange, yellow, green, blue and violet, you might see just a pale, faint arc, sometimes tinged with colour at the edges but mostly white. Fogbows are subtle, delicate, and they require the right conditions: bright sunlight, thick fog or mist, and a dark background to see them against. The smoothness of a rainbow can come from having many droplets in many positions. A perfect smooth arc happens when there are countless droplets all at the right angles, all working together to create a continuous band of light. If the rain is uneven, if there are gaps in the shower, or if the droplets are scattered in clusters, the rainbow can look patchy or incomplete. You might see a bright section here, a faint section there, an empty sky in between. A rainbow may look patchy if the rain is uneven or the sunlight is intermittent. Clouds moving across the sun can dim the rainbow suddenly, or make it flicker as the light comes and goes. A passing shower might create a rainbow that lasts only a minute or two before the droplets drift away or evaporate. Rainbows can appear and disappear as clouds shift and droplets move. They're tied to the moment, to the specific arrangement of sun, water and observer, and when any of those elements change, the rainbow changes too. Even when it changes, the rainbow follows the same calm rules of geometry. The physics doesn't shift. The angle is always 42 degrees for the main arc. The colours always appear in the same order, determined by wavelength. The anti-solar point is always opposite the sun, relative to your eyes. These rules are constant, reliable, like a quiet rhythm underlying the visible changes. A rainbow is like a momentary window where light and water agree on the same angle. That's a gentle way to think about it. For a brief period, the sun is in the right position, the droplets are in the right position, and you're in the right position, and those three elements align to create the view. It's not magic, but it's special, because it requires that alignment. Move a little, wait a little, and the window closes. The rainbow fades, and the sky returns to its usual state. With droplet size in mind, we can gently explore the idea that your rainbow is personal, because it depends on where you are standing. Each observer sees a rainbow from their own unique viewpoint. This is one of the most interesting aspects of rainbows, and it's worth taking time to understand it fully. The rainbow you see is made by droplets sending light toward your eyes at the right angles. Those droplets are in specific positions in the sky, at exactly the right distance and height to create the 42-degree angle from the anti-solar point to your eyes. Someone standing a few steps away sees light from different droplets. Their anti-solar point is in a slightly different position, because it's defined by the line from the sun through their eyes, and the droplets at the right angle from their anti-solar point are different droplets than the ones at the right angle from yours. So even though you're both looking at the same patch of sky, the light reaching your eyes is coming from different sources. You're each seeing your own rainbow built from different droplets, the anti-solar. Point depends on the position of your eyes. It's not a fixed point in the sky, it's relative to you. If you move, the anti-solar point moves with you, and the rainbow seems to move too. This can make rainbows feel like they're following you, though it's just geometry. You're not chasing the same rainbow, you're continuously seeing new rainbows, each one built from the droplets that are currently at the right angle from your new position. Rainbows can appear in sprays from waterfalls or fountains for the same reason. The same optical principles apply. Sunlight, water droplets in the air, the right angle. That's all you need. At a waterfall, the mist thrown up by the falling water can create a rainbow if the sun is shining and you're standing at the right spot. Fountains can do the same thing, and garden sprinklers too. If you've ever stood near a sprinkler on a sunny day and seen a little arc of colour in the spray, you've seen the same process at work. It's a miniature rainbow, following the same rules, just on a smaller scale. It's a quiet reminder that perception is a partnership between the world and your point of view. The rainbow isn't just out there, independent of you. It exists because you're there to see it, because your eyes are in the right position to receive the light. Another person sees a different rainbow. A camera sees yet another rainbow, depending on where it's placed. The world provides the sunlight and the droplets, but the rainbow you see is shaped by where you stand, where you look, and how your eyes interpret the light. Now we'll broaden gently into other kinds of rainbow-like effects, halos, glories, and light patterns that also come from tiny particles in the air. Rainbows aren't the only optical phenomena created by light interacting with particles. The sky is full of these effects, most of them subtle, many of them rarely noticed, but all of them following similar principles, light bending, reflecting, diffracting, and interfering in predictable ways. Halos around the sun or moon are often caused by ice crystals rather than raindrops. When the air is cold enough high up in the atmosphere, water vapour freezes into tiny ice crystals instead of forming liquid droplets. These ice crystals are often hexagonal, six-sided prisms, and they refract light differently than spherical droplets do. When sunlight or moonlight passes through these crystals, it bends, and the bending creates rings or arcs around the light source. A halo can look like a bright circle surrounding the sun or moon, sometimes with a radius of 22 degrees, sometimes 46 degrees, depending on the path the light takes through the crystals. These halos can form rings, arcs, or bright spots in the sky. The shapes depend on the orientation of the ice crystals and the path of the light. If the crystals are randomly oriented, you get a full ring. If they're aligned in a particular way, you might see arcs, or bright spots called sundogs or parhelia. Sundogs appear as bright patches of light on either side of the sun, often tinged with colour, and they're caused by light refracting through horizontally oriented ice crystals. A glory is a set of coloured rings, sometimes seen around a shadow, often from airplanes. If you've ever looked down from a plane and seen your shadow on the clouds below, you might have noticed coloured rings surrounding it. That's a glory. It's caused by light being scattered and reflected by tiny droplets in the clouds, and it requires a very specific geometry. The light source behind you, a cloud of droplets in front of you, and your shadow visible on the cloud. The rings are usually concentric, with colours that can shift depending on the size of the droplets. Glories happen when light is scattered and reflected by tiny droplets in clouds. The exact mechanism is complex and involves a phenomenon called backscattering, where light enters a droplet, bounces around inside and exits back toward the source. The droplet size affects the spacing and colours of the rings, and because cloud droplets are very small, the glory can be quite vivid. Sundogs are bright spots that appear beside the sun under certain ice crystal conditions. They're one of the more common halo phenomena, and if you know what to look for, you can spot them fairly often, especially in cold weather when high cirrus clouds are present. Sundogs can be quite bright, sometimes bright enough to be mistaken for a second sun, and they're often tinged with red on the side closest to the sun and blue on the side farther away. These effects show how different particle shapes produce different light patterns. Spherical water droplets create rainbows. Hexagonal ice crystals create halos and sundogs. Tiny cloud droplets create glories. The shape, size, and orientation of the particles all matter, and they all affect how light bends, reflects, and spreads. Rainbows are strongly linked to spherical water droplets. The geometry of a sphere is what creates the 42-degree angle and the circular arc. Change the shape to a hexagon, and you get different angles, different arcs, different phenomena. Ice crystals tend to make sharper geometric patterns, like halos and arcs. Because they're crystalline with flat faces and specific angles, the light interacts with them in precise ways. The refraction happens at defined angles, 22 degrees, 46 degrees, and the result is geometric shapes in the sky, arcs and rings and spots, all following the symmetry of the crystal. The sky often contains invisible structures of light until the right conditions reveal them. On a clear day, you might not see anything unusual, but the light is still there, bending and scattering in the atmosphere, just waiting for the right particles, the right observer, the right angle. Add some mist, some ice crystals, some rain, and suddenly the invisible becomes visible, the hidden patterns of light appear, and the sky shows you its quiet artistry. In a sleepy way, it's comforting to know the atmosphere can be quietly beautiful without trying. These phenomena aren't created for us. They're not performances or displays. They're just the natural behaviour of light and particles, following physical laws, creating patterns because that's what light does when it meets certain conditions. And yet we get to see them, and appreciate them, and find beauty in them. It's a gift that requires nothing from us except to be there, to look up, to notice. Now we'll return from sky cousins back to the familiar rainbow and settle it into bedtime calm. Simple rules, soft colours, and no urgency. Rainbows are not objects located over there. They are views of light at an angle. It's worth repeating this because it's central to understanding what a rainbow is and isn't. A rainbow doesn't have a location in the usual sense. You can't point to it and say it's 100 meters away or a kilometer or 10 kilometers. The droplets creating the rainbow might be at various distances, but the rainbow itself is defined by the angle, not the distance. You can't walk to the end of a rainbow because the rainbow depends on your viewpoint. There's an old myth about a pot of gold at the end of the rainbow, and it's charming, but it's geometrically impossible. As you walk toward where the rainbow appears to be, the anti-solar point moves with you, and the rainbow moves too. You're always seeing light from droplets at the 42-degree angle from your current anti-solar point, so the rainbow stays the same apparent distance away, always just out of reach. Rainbows do not require special magic. They require sunlight, water droplets, and the right geometry. That's all. The conditions are specific but not rare. After a rainstorm, when the sun comes out and there are still droplets in the air, the chance of a rainbow is high. You need the sun behind you, rain or mist in front of you, and a clear, enough sky that the sunlight can reach the droplets. If those conditions are met, a rainbow can form. The sun needs to be behind you for a classic rainbow to appear in front of you. This is because the light has to come from behind, pass through the droplets in front and then reflect back toward you. If the sun is in front of you, the geometry doesn't work. The light exits the droplets away from you, and you don't see the rainbow. So the basic setup is always the same. Sun behind, rain ahead. Rainbows often appear after rain showers when the sky begins to clear. The classic rainbow moment is when a storm is passing, the rain is easing, and the sun breaks through from behind. The sky ahead is still dark with clouds and lingering rain, and the light from behind catches the droplets at just the right angle. Those are the conditions that create the brightest, most vivid rainbows. The contrast between the dark clouds and the bright arc of colour. A low sun angle usually helps create a higher, more visible arc. When the sun is near the horizon, the anti-solar point is high in the sky, and the rainbow can stretch up in a tall, prominent arc. Late afternoon and early evening are prime times for rainbows, as are early mornings, because the sun is low, and if there's been a shower, the conditions are right. The best rainbow backgrounds are often darker clouds, which make colours stand out. A rainbow against a bright, hazy sky can be hard to see. The colours get washed out by the surrounding light, but a rainbow against a dark storm cloud is vivid and clear. The colours sharp, the arc distinct. The contrast makes all the difference. If the sunlight dims or the droplets disperse, the rainbow fades naturally. Rainbows are temporary because the conditions are temporary. The sun moves, the clouds shift, the rain stops, the droplets evaporate or fall to the ground. As the conditions change, the rainbow fades. It's not a sudden disappearance usually, but a gradual dimming, the colours softening, the arc becoming less distinct until it's gone. The fading isn't a loss, it's simply the conditions changing. There's something peaceful about that. The rainbow appears when the conditions are right, and it fades when they're not. It doesn't struggle to stay, it doesn't resist the change, it simply is, and then isn't, and that's enough. Rainbows remind us that beauty can be brief and still complete. A rainbow doesn't need to last an hour to be beautiful. A few minutes is enough, a glimpse is enough. The brevity doesn't diminish it, if anything it enhances it, makes it feel more special, more worth noticing. And because rainbows follow predictable rules, they're also reliable. If the conditions are right, a rainbow will appear. It's not random, it's physics. And that's a kind of comfort too, knowing that the same rules always apply, that the same causes always produce the same effects. To continue our gentle exploration, we can think about how rainbows have been understood throughout history. People have been seeing rainbows for as long as there have been people, and for most of that time the mechanism remained mysterious. Ancient cultures saw rainbows and created stories to explain them. In Greek mythology, the rainbow was personified as Iris, a messenger goddess who travelled between the mortal world and the realm of the gods. The rainbow was seen as a bridge, a pathway between earth and sky. In Norse mythology, the rainbow bridge Bifrost connected Midgard, the world of humans, to Asgard, the realm of the gods. These stories reflect a sense that rainbows are liminal phenomena, existing between worlds, between states. For a long time, the physical explanation remained out of reach. Aristotle, the Greek philosopher, wrote about rainbows in his work Meteorology around 350 years before the Common Era. He understood that rainbows had something to do with the sun and with water in the air, and he recognized that the observer's position mattered. But he didn't have the concept of light as something that could be refracted or dispersed. His explanation involved reflections from individual droplets, but he couldn't quite piece together the full mechanism. It wasn't until the 17th century that the optical explanation began to take shape. René Descartes, the French philosopher and mathematician, made significant progress in understanding rainbows in the 1630s. He used geometry to trace the path of light through a spherical water droplet, and he discovered the importance of the 42-degree angle. Descartes performed experiments with glass spheres filled with water, tracing how light entered, reflected, and exited, and he was able to explain why rainbows formed arcs at specific angles. His work was a major step forward, though he still didn't fully understand dispersion, the spreading of white light into colours. That piece of the puzzle came from Isaac Newton. In the 1660s, Newton performed his famous prism experiments, showing that white light could be split into a spectrum of colours and that those colours could be recombined back into white light. He demonstrated that colour was a property of light itself, not something added by the prism or the water. Different wavelengths of light, he showed, refracted by different amounts, and that was the key to understanding the rainbow's colours. Newton's work on optics, combined with Descartes' geometric analysis, gave us the complete explanation of rainbows that we still use today. It's remarkable to think that for thousands of years, people saw rainbows without understanding them, and yet they still found them beautiful. The beauty didn't depend on the explanation. The rainbow was compelling whether you thought it was a goddess, a bridge, or a pattern of refracted light. And now, with the explanation in hand, the beauty remains. If anything, understanding the mechanism adds another layer of appreciation. You can look at a rainbow and see not just colours but geometry, not just an arc but countless droplets working together, not just light but wavelengths separated and displayed. We can also think about how rainbows interact with the landscape around them. A rainbow doesn't exist in isolation. It appears against a background, and that background shapes how we see it. A rainbow over mountains looks different from a rainbow over the ocean. The mountains provide contours, peaks that the arc seems to touch or cross. The ocean provides a flat, continuous surface, and a rainbow over water can create a reflection, doubling the effect. If the water is calm and reflective, you might see the rainbow itself and a mirrored image of it in the water below, creating a symmetry that amplifies the sense of order and balance. Rainbows can also appear in the spray near waterfalls, and these rainbows have a particular charm. The waterfall creates a constant mist, and if the sun is in the right position, the rainbow can seem to hover near the falling water, steady and persistent. Unlike a rainbow from a passing shower, which fades as the rain moves on, a waterfall rainbow can last as long as the sun and the mist are both present. You can stand there and watch it, and it feels almost stationary, even though the droplets creating it are constantly being replaced by new ones. In some places, the conditions for rainbows are more common than others. Tropical regions, where rain showers are frequent and intense, and where the sun often breaks through between storms, can produce rainbows regularly. In Hawaii, for instance, rainbows are so common that they've become part of the local identity, appearing on license plates and in cultural imagery. The frequent interplay of sun and rain, the trade winds pushing clouds across the islands, and the dramatic topography all contribute to ideal rainbow conditions. At higher latitudes, rainbows are less frequent but perhaps more striking when they do appear. The lower angle of the sun in northern or southern regions can create very tall arcs, and the seasonal changes mean that rainbows have different characters at different times of year. A winter rainbow, appearing in cold, clear air after a brief shower, can have a sharpness and clarity that's different from a summer rainbow seen through humid, hazy air. The time of day also affects the rainbow's appearance. Morning rainbows form when the sun is low in the east and the rain is to the west. Evening rainbows form when the sun is low in the west and the rain is to the east. The light quality differs between morning and evening. Morning light tends to be cooler and clearer, while evening light is warmer and often more golden. These differences can subtly affect the rainbow's colours, adding a warm tint to an evening rainbow or a cooler, crisper feel to a morning one. We can think too about the experience of seeing a rainbow. There's often a moment of surprise. Even if you've seen many rainbows before, you step outside after a storm or you look up while driving and there it is, an arc of colour where there was just sky before. The surprise comes partly from the rarity, the sense that this is a special alignment of conditions, and partly from the vividness, the way the colours stand out against the clouds. There's also a contemplative quality to watching a rainbow. Because rainbows are temporary, because they fade, there's a built-in incentive to pause and look. You can't save it for later. You can't come back tomorrow and find the same rainbow still there. So you stop, you watch, and for a few moments the ordinary concerns of the day recede. The rainbow doesn't ask anything of you. It doesn't require interpretation or response. It just is, and you can just be with it, letting the colours fill your vision, letting the geometry settle in your mind. Photographs of rainbows are common, but they rarely capture the full experience. A photograph flattens the scene, reducing the three-dimensional sky to a two-dimensional image. It can show the colours and the arc, but it can't convey the sense of scale, the feeling of standing beneath a huge arc that stretches from horizon to horizon. It can't capture the way the rainbow seems to move when you move, or the subtle shifts in brightness as clouds pass, or the quiet satisfaction of understanding what you're seeing. And yet, even a photograph can bring a sense of calm. Looking at an image of a rainbow, you remember the experience of seeing one, and that memory carries some of the same peaceful qualities. The colours are soothing, the arc is orderly, and the context, a clearing storm, sunlight breaking through, suggests resolution, the end of turbulence, a return to calm. Now, we can turn our attention to the broader physics of light and colour, the deeper principles that make rainbows possible. Light is electromagnetic radiation, a wave of electric and magnetic fields, oscillating together, travelling through space at constant speed. The wavelength of this oscillation determines the colour we perceive. Red light has a wavelength of about 700 nanometers, 700 billionths of a meter. Violet light has a wavelength of about 400 nanometers. In between are all the other colours: orange, yellow, green, blue, each with its own specific wavelength. The visible spectrum, the range of wavelengths our eyes can detect, is just a small slice of the full electromagnetic spectrum. Beyond red, there's infrared radiation, with longer wavelengths that we feel as heat but can't see. Beyond violet, there's ultraviolet radiation, with shorter wavelengths that can cause sunburn but are invisible to our eyes. Rainbows show us only the visible portion, the part of the spectrum our biology has evolved to detect. The reason different wavelengths refract differently has to do with how light interacts with matter at the atomic level. When light enters a material like water, it interacts with the electrons in the water molecules. These interactions slow the light down, and the amount of slowing depends on the wavelength. Shorter wavelengths interact more strongly, slow down more, and therefore bend more. Longer wavelengths interact less strongly, slow down less, and bend less. This wavelength-dependent bending is what creates dispersion, and dispersion is what creates the rainbow's colours. Water is particularly good at creating rainbows because it's transparent, it forms spherical droplets, and it has the right refractive properties. Other liquids can create similar effects, but water is ubiquitous, especially in the atmosphere, so water rainbows are what we usually see. Glass can also create rainbows. A glass prism works on the same principle, refracting and dispersing light, but glass doesn't naturally form spherical droplets hanging in the air, so glass rainbows are usually human-made, seen in laboratories or in decorative. Crystals hung in windows. The concept of the refractive index helps quantify how much light bends in a material. The refractive index is a number that describes how much slower light travels in a material compared to its speed in a vacuum. Water has a refractive index of about 1.33, meaning light travels about 1.33 times slower in water than in a vacuum. Air has a refractive index very close to 1, meaning light travels almost as fast in air as in a vacuum. When light crosses from air to water, the speed change is significant, and that's what causes the bending. The refractive index isn't exactly the same for all wavelengths. This variation is called dispersion, and it's what causes the spreading of colours. For water, the refractive index for red light is slightly lower than for violet light, about 1.331 for red and 1.343 for violet. The difference seems small, but it's enough to create the spread of colours we see in a rainbow. Inside the raindrop, the geometry is everything. The spherical shape means that light entering from different parts of the droplet will reflect at different angles. But because of the curvature, there's a particular set of paths where the light is concentrated, where many rays of light end up exiting in nearly the same direction. This concentration creates the bright band we see as the rainbow. The 42-degree angle for the main rainbow is the angle where this concentration is strongest. Mathematically, this can be derived by tracing rays of light through a sphere, calculating how they refract on entry, reflect inside, and refract again on exit, and then finding the angle where the exiting rays cluster together. The calculation involves trigonometry and calculus, but the result is precise. 42 degrees for one internal reflection, 51 degrees for two reflections, and so on for higher order rainbows, though those are much fainter and rarely seen. Higher order rainbows do exist, at least in theory. A third order rainbow would require 3 internal reflections, and it would appear at a different angle, closer to the sun rather than opposite it. Fourth order, fifth order, and even higher rainbows are possible, each requiring more reflections, each getting fainter because each reflection loses light. In practice, these higher order rainbows are almost never visible because they're so dim and because the geometry places them in parts of the sky where the bright light from the sun drowns them out. But in carefully controlled conditions or in photographs with long exposures, higher order rainbows have been captured. They're faint, often just barely visible, but they're there, following the same laws of optics, obeying the same geometric rules, just pushed to the limits of detectability. Their existence is a reminder that the physics doesn't stop at the rainbows we commonly see. The same processes continue, creating fainter and fainter arcs, each one a testament to the consistency of natural law. We can also think about polarization, another property of light that affects rainbows. Light is a wave, and the wave can oscillate in different directions perpendicular to its direction of travel. Unpolarized light oscillates in all directions. Polarized light oscillates in just one direction. When light reflects off a surface, it often becomes partially polarized. In a rainbow, the light has reflected inside the droplet, and this reflection polarizes it. If you look at a rainbow through a polarizing filter, like the ones in some sunglasses, and rotate the filter, the rainbow can brighten or dim depending on the filter's orientation. This happens because the filter blocks light oscillating in one direction and transmits light oscillating perpendicular to that. When the filter is aligned with the rainbow's polarization, the rainbow looks bright. When it's perpendicular, the rainbow dims. It's a subtle effect, but it's there. Another layer of structure hidden in the light. The colours of a rainbow can also be affected by the presence of other particles in the air. Dust, pollution, or smoke can scatter light, adding a haze that mutes the colours or shifts their appearance. A rainbow seen through clean, clear air after a fresh rain tends to be more vivid than one seen through dusty or polluted air. The scattering from the extra particles adds a diffuse background light that washes out the contrast. In some cases, additional optical effects can appear alongside a rainbow. Supernumerary bows are faint, pastel-coloured bands that sometimes appear just inside the main rainbow, running parallel to it. They're caused by interference, the wave nature of the light causing different paths to add together or cancel out. Supernumerary bows require very uniform droplet sizes to be visible, and they're delicate, often just barely noticeable. But when conditions are right, they add an extra layer of detail to the rainbow. There's also the phenomenon of twinned rainbows, where two rainbows appear to emerge from the same base but split apart as they rise. This can happen when raindrops aren't quite spherical, or when there are two populations of droplets with slightly different sizes or shapes. The result is a rainbow that looks doubled, not concentrically like a primary and secondary rainbow, but side by side sharing a common origin. All of these variations, supernumerary bows, twinned rainbows, higher order rainbows, are subtle and most people never notice them. But they're there, following the same underlying physics, adding complexity and richness to what might seem like a simple phenomenon. Rainbows are simple in principle: light, water, geometry, but they're endlessly complex in detail. We can also think about rainbows in different contexts beyond Earth's atmosphere. Rainbows require liquid droplets and sunlight, so anywhere with those ingredients can produce rainbows. On Earth, that's primarily rain, but it can also be sea spray, waterfall mist, or even the spray from a breaking wave. On other planets, the conditions would be different, but the principle would be the same. On a planet with a different atmosphere or a different kind of liquid, the rainbow would look different. The refractive index would be different, so the angles would change. The light from the planet's star might have a different spectrum, so the colours would shift. But the basic mechanism, light refracting, reflecting, dispersing through droplets, would still apply. A rainbow on Titan, Saturn's moon, where liquid methane rains from the sky, would follow the same optical laws, but with methane's refractive properties instead of water's. Even on Earth, the sun isn't the only light source that can create rainbows. The moon can create rainbows too, called moonbows or lunar rainbows. They're rare because moonlight is much dimmer than sunlight and the human eye doesn't see colours well in low light. A moonbow often looks white or very faintly coloured, more like a fog bow, because our eye's colour receptors need a certain amount of light to function. But photographs taken with long exposures can capture the colours in a moonbow, showing that the full spectrum is there, just too dim for our eyes to perceive directly. Artificial light sources can also create rainbows. A streetlight shining on a fountain at night can produce a small rainbow in the spray. Floodlights at a stadium can create rainbows in the mist from sprinklers. The light source doesn't have to be the sun, it just has to be bright enough and positioned correctly. This means that rainbows aren't confined to natural settings. They can appear in cities, in parks, anywhere water droplets and light come together. There's something democratic about this. Rainbows aren't reserved for wilderness or remote locations. They can appear in your backyard, in a city square, even in the spray from a car wash. The beauty is accessible, tied to simple physical principles that operate everywhere. You don't need to travel to a special place to see a rainbow. You just need the right combination of light and water, and a moment to look. As we continue to settle into this gentle exploration, we can think about the emotional and cultural resonance of rainbows. Beyond the physics, beyond the geometry, rainbows carry meaning for people. They're seen as symbols of hope, of promise, of beauty emerging from difficulty. This symbolism isn't arbitrary, it's rooted in the context where rainbows appear. They come after storms, when the rain is ending and the sky's clearing. They mark a transition from turbulence to calm, from grey to colour. In the biblical story of Noah's Ark, the rainbow is a sign of God's promise not to flood the earth again. It's a symbol of covenant, of reassurance. In more secular contexts, rainbows are associated with diversity and inclusion, the spectrum of colours representing the spectrum of human identity. The pride flag, with its rainbow stripes, draws on this symbolism, using the rainbow as an emblem of acceptance and celebration. These cultural meanings layer onto the physical phenomenon, adding depth and richness. When you see a rainbow, you're not just seeing refracted light. You're seeing something that connects to stories, to symbols, to shared human experience. The rainbow can mean something different to different people, and all of those meanings coexist with the scientific explanation. Understanding the optics doesn't diminish the symbolism. If anything, it enriches it, adding another dimension of appreciation. We can also think about the aesthetic pleasure of rainbows, the simple visual delight they provide. The colours are bright but not harsh, spread across the sky in an orderly arc. The shape is pleasing, a smooth curve that the eye can follow from one end to the other. The contrast with the background, especially a dark cloud, creates visual drama without aggression. It's beauty that's bold enough to notice but gentle enough to contemplate. There's also the scale. A rainbow can span half the sky, an enormous arc that dwarfs buildings and trees. Standing beneath it, you feel small, but not oppressively so. It's a reminder of the vastness of the atmosphere, the reach of light, the scale of natural processes. And yet at the same time, a rainbow is delicate. easily disrupted, here one moment and gone the next. That combination of grandeur and fragility is part of its appeal. Artists have been painting rainbows for centuries, trying to capture their appearance on canvas. It's a difficult subject because the colours blend so smoothly and because the rainbow doesn't have sharp edges or clear boundaries. Some artists emphasise the arc, making it bold and distinct. Others blur it, making it soft and atmospheric. Some include the full context, the storm clouds, the landscape, the changing light, while others focus tightly on the rainbow itself. Each approach captures a different aspect of the experience, a different way of seeing. Photographers face similar challenges. A rainbow in a photograph can look vivid and clear, or it can look washed out and faint, depending on exposure and contrast. Wide-angle lenses can capture the full arc, while telephoto lenses can zoom in on details, showing the colour gradations or the texture of the background clouds. Double rainbows are particularly striking in photographs, the two arcs creating a sense of symmetry and balance. But whether painted or photographed, or simply remembered, the rainbow retains a certain ineffable quality. It's hard to fully capture the experience of standing in the open air, the rain smell still lingering, the sun warm on your back, and seeing that arc of colour stretch across the sky. The experience is more than visual. It's sensory, emotional, temporal. It's about the moment, the unexpectedness, the brief alignment of conditions that brings the rainbow into being. In thinking about time, we can consider how long a rainbow lasts. Some rainbows appear for just a minute or two, visible only while the sun, the rain, and the observer remain in the right alignment. Others can last much longer, especially if the rain is steady and the sun remains uncovered. A rainbow might persist for 10 minutes, 15, even half an hour in some cases, slowly shifting and changing as the droplets move and the light changes. The longest rainbows occur when the conditions are stable, a steady light rain, a stationary sun angle, minimal wind to disperse the droplets. In such cases, the rainbow can seem almost permanent, though of course it's always being recreated moment by new droplets moving into the right positions as old ones fall away. It's like a river in that sense. It looks the same, but the water is constantly changing, constantly being replaced. Time of year affects rainbows too. In regions with distinct seasons, rainbows are more common at certain times. Spring and fall, with their mix of sun and rain, their changeable weather, often produce more rainbows than summer or winter. Summer can be too dry, or the rain too heavy and prolonged, without breaks for the sun to shine through. Winter can be too cold, with precipitation falling as snow instead of rain, or the sun too low and weak to create bright rainbows. But when winter rainbows do occur, they can be particularly striking. The air is clear, the light is crisp, and the low sun angle creates very tall arcs. A winter rainbow over a snowy landscape, the white ground contrasting with the coloured arc, can be visually stunning, a rare combination of conditions that photographers and weather enthusiasts seek out. We can also think about the future of rainbows in a changing climate. As the Earth's atmosphere warms, weather patterns are shifting. Some regions are getting more rain, others less. Storm tracks are changing and the frequency of different weather conditions is shifting. How will this affect rainbows? It's a small question in the larger context of climate change, but it's worth pondering. In regions where rain becomes less frequent, rainbows will become rarer. In places where storms become more intense but briefer, the windows for rainbows might remain, occurring in those moments when the storm clears and the sun breaks through. The basic physics won't change. Light will still refract through water droplets at the same angles, but the frequency and distribution of rainbows could shift along with the weather. There's also the question of air quality. Cleaner air produces clearer, more vivid rainbows. Polluted air can dull them. Efforts to reduce air pollution could make rainbows more vibrant in some regions. On the other hand, increased dust from droughts or desertification could have the opposite effect. These are subtle impacts, but they're real. The atmosphere is a system, and changes to one part of it ripple through to affect others. Even something as simple and beautiful as a rainbow is connected to larger environmental trends. It's a reminder that everything is interconnected, that the light we see has travelled through an atmosphere shaped by countless factors: temperature, humidity, pollution, weather patterns, all of which are influenced by human activity and natural cycles. But let's return to the immediate, to the experience of seeing a rainbow on a quiet evening after a storm. The science explains the how, but it doesn't diminish the why. Why we find it beautiful, why we stop to look, why it brings a moment of peace. The rainbow is a pattern, an emergent property of simple rules applied to millions of droplets. It's order arising from randomness, structure emerging from chaos. The droplets aren't organised. They're just falling, drifting, evaporating. But the light passing through them finds the order, picks out the angles, and creates something coherent and beautiful. This is true of many natural phenomena. Snowflakes, with their six-fold symmetry, arise from the molecular structure of water and the conditions in which they form. Waves on the ocean, rolling in parallel lines toward the shore, arise from the wind transferring energy to the water. Clouds forming in rows across the sky arise from atmospheric instabilities and wind patterns. None of these things are designed or planned. They're the natural outcome of physical processes, and yet they have a beauty that feels almost intentional. Rainbows fit into this category. They're not made for us, but they exist because of us, because we're here to see them, because our eyes detect the wavelengths of visible light, because our brains interpret those wavelengths as colour. A rainbow is a collaboration between the world and the observer, between physics and perception, and in that collaboration, there's a kind of gift. The world doesn't owe us beauty, but it provides it anyway, as a byproduct of its ordinary functioning. Light refracts because that's what light does when it changes speed. Water forms droplets because of surface tension. The sun shines because of nuclear fusion in its core. None of these processes are concerned with creating rainbows, and yet, when they intersect in the right way, a rainbow appears, and we get to see it and find it beautiful and carry that beauty with us. As we move toward the close of this gentle journey through the science and experience of rainbows, we can let the ideas settle, like droplets falling from the sky and coming to rest. The arc in the sky is made of countless small contributions, each droplet doing its part, bending a little light, reflecting it, sending it on its way. Together they create something that none of them could create alone, a spectrum, a curve, a moment of colour against the clouds. The geometry is simple. Angles, circles, the relationship between the sun and the observer. The physics is elegant, wavelengths, refraction, dispersion. The experience is rich, surprise, contemplation, a sense of connection to the natural world. All of these layers coexist in the rainbow, each one adding depth to the others. When you see a rainbow, you're seeing a very specific arrangement of the world. The sun is behind you at a certain angle. Rain or mist is ahead of you at the right distance. Your eyes are positioned to receive the light that has bounced through millions of droplets, each one contributing a tiny piece of the pattern. It's a coincidence in a way, all these conditions coming together, but it's also inevitable. Given enough time, enough weather, the conditions will align. Rainbows are rare in any given moment, but common across time and place, and because they're temporary, because they fade, they teach a gentle lesson about impermanence. The rainbow doesn't cling to existence. It doesn't fight the changing conditions. When the rain stops, or the sun moves, or the clouds shift, the rainbow simply fades. It was here, and now it isn't. And that's the natural rhythm of things. Appearances and disappearances, formations and dissolutions, the constant flow of conditions creating temporary patterns. You can apply this to thoughts, to feelings, to experiences. They arise, they persist for a time, and they fade. You don't have to hold on to them or push them away. You can let them be, observe them, appreciate them if they're pleasant, tolerate them if they're not, and let them pass when they're ready. Like colours in a rainbow, each one has its place, its moment, and then it blends into the next and eventually fades into the background. Tonight, as you prepare for sleep, you can imagine yourself standing beneath a rainbow that exists only in your mind's eye. The colours are soft, red fading to orange, orange to yellow, yellow to green, green to blue, blue to violet. The arc is gentle, curving from one side of your inner horizon to the other. The background is a quiet grey-blue, the colour of evening, the colour of calm. The rainbow is bright but not demanding. It's just there, a presence, a pattern of light. As you breathe slowly, the rainbow begins to fade. The colours soften, blending more and more with the background. The red becomes a pale pink, the violet a soft lavender. The whole arc grows dimmer, gentler, less distinct. The edges blur. The spectrum becomes a hint, a memory, a whisper of colour against the quiet sky. And then it's gone, and the sky is just sky, peaceful and still. And you're left in that stillness, that quiet space where the rainbow was. There's no absence, no loss, just a return to calm. The light has moved on, the droplets have dispersed, and the conditions have changed. But the experience remains, the understanding remains, the sense of connection to something larger and quieter than the busy day. A rainbow is made from countless tiny droplets cooperating with sunlight. Each droplet contributes a small piece of colour to the whole arc. The rainbow's curve is a calm consequence of consistent angles. The colours are a quiet reminder that white light holds many possibilities inside it. A double rainbow shows that even an extra reflection can create a new soft pattern. Your rainbow is yours because your viewpoint matters in what you perceive. Rainbows arrive when conditions are right and leave when conditions shift. That gentle arriving and leaving is part of their comfort. And now, as the gentle exploration comes to its natural close, you can let the words fade like the rainbow itself. Let the ideas settle into quiet understanding. Let the colours blend back into the background of your mind. The science is there if you want to recall it. The refraction, the reflection, the dispersion, the 42-degree angle, the anti-solar point. But you don't need to hold on to it actively. It can rest quietly in your memory, ready to emerge when you see a rainbow again, adding depth to the experience without demanding attention. For now, you can simply rest, in the knowledge that the world follows patterns, that light and water create beauty through simple, consistent rules, and that you are part of that pattern, an observer whose position and perception complete the phenomenon. The rainbow needs you as much as it needs the sun and the rain. Without an observer, the light would still refract and reflect, but there would be no rainbow, just scattered light going nowhere in particular. You complete the circuit, you close the loop, you make the rainbow real by being there to see it. And in that role, in that quiet participation, there's a kind of peace. You don't have to do anything. You don't have to make the rainbow happen or keep it going. You just have to be there, eyes open, mind receptive, ready to receive the light. And when the light comes, when the colours appear, you can appreciate them, let them fill your vision, let them remind you that the world is capable of beauty, that simple processes can create complex and moving results. That order and colour can emerge from the everyday interaction of sunlight and water. Take a slow breath in, feeling the air fill your lungs, and then let it out slowly, releasing any remaining tension. Imagine that soft arc of colour one more time. Red on the outside, violet on the inside, the colours blending smoothly across the sky. See it there in your mind, complete and whole, asking nothing of you, just being what it is. And as you watch, let it gently fade, the colours softening, the arc dimming, until it's just a faint suggestion against the quiet evening sky. And then it's gone, and you're left in peace, in stillness, in the calm that comes after the storm has passed and the light has moved on. The rainbow was here, and now it isn't, and that's exactly as it should be. Everything that appears will fade, every colour will blend back into the background, every arc will soften into sky. And you can rest in that knowledge, let it comfort you, let it ease you into sleep. The world will continue, light will continue to refract and reflect, rainbows will continue to appear and fade, and you can let go of your hold on the moment, let go of your need to preserve or understand or remember, and simply drift into the quiet, peaceful darkness of sleep, where even the memory of rainbows fades into dreams and dreams fade into rest, and rest is all there is. The next story is about to begin. Please relax and enjoy. Saturn's rings are a wide, thin disk of countless small particles orbiting the planet, and when you picture them from far away, they look almost solid, like a great shining band wrapped around the pale yellow globe. But if you could drift closer, slowly enough to see the details emerge, you'd realise that what seemed like a single structure is actually more like a drifting swarm of icy pieces, each one following its own quiet path through space. Most of these ring particles are made largely of water ice, which is part of why the rings look so bright when sunlight touches them. Water ice is remarkably good at reflecting light, so even though the rings are made of separate fragments, they shine back at us with a steady, cool glow that makes them visible across the vast distance between Saturn and Earth. The particles themselves come in many sizes. Some are as small as grains of sand or tiny pebbles, barely larger than a speck of dust. Others are bigger, perhaps the size of a snowball, or even a boulder. A few might be as large as a small house, though these are rare. The important thing is that none of them are permanently stuck together into one solid object. Instead, they orbit Saturn individually, each one held in place by gravity, following a stable path like cars moving in gentle lanes around a roundabout. The rings themselves don't spin as one piece. They're more like a collection of travellers all going in the same general direction, but each at their own speed, depending on where they are. Saturn is not the only planet with rings. Jupiter has rings, and so do Uranus and Neptune, but Saturn's rings are by far the most bright and dramatic to see. They're the ones that catch your attention when you look at images of the outer solar system, the ones that make Saturn instantly recognisable. The rings are extremely wide compared to how thin they are. If you imagine the rings as a giant sheet of paper spread around a globe, you'd have a sense of their proportions. They stretch out for hundreds of thousands of kilometres across, but in many places they're only a few metres thick, sometimes just tens of metres, sometimes even less. That thinness is part of what makes them so delicate and beautiful. From certain angles, the rings can nearly disappear. This happens when we're looking at them edge-on, when the thin disk is oriented so that we're seeing it from the side rather than from above or below. At those times, the rings become almost invisible, like a line so fine it's hard to detect even with a good telescope. But when the angle changes again, when Saturn's orientation shifts in its orbit, and we can see the rings tilted toward us, they reappear in all their brightness, and the effect is almost magical, as if the planet had opened a quiet fan of light. The rings are not perfectly smooth. If you could look closely enough, you'd see that they have bands, gaps, and delicate textures. Some regions are bright and densely packed with particles, while others are darker and more translucent. There are divisions where the material thins out or nearly vanishes, and there are places where the particles seem to gather more thickly, like snow piling up in certain drifts. A calm way to picture the rings is as a quiet halo made of ice, turning slowly in sunlight, reflecting back a steady glow that speaks to the gentle order of orbital motion. Let's drift a little closer now, like we're floating above the ring plane, noticing how the ring system is organised into named sections. Saturn's main bright rings are commonly labelled the A, B and C rings, and these labels come from the order in which astronomers discovered and identified them, not necessarily from their position. The B ring is generally the brightest and most dense of the main rings. It's the one that stands out the most when you look at Saturn through a telescope, the region where the particles are packed closely enough that the ring looks almost solid. The B ring reflects a lot of sunlight, and it has a thickness to its appearance, a kind of visual weight that makes it the centerpiece of the whole ring system. The A ring is outside the B ring, farther from Saturn, and it contains many fine structures and narrow gaps. It's bright as well, though not quite as intensely packed as the B ring, and when you study it closely, you can see that it has layers of detail, small divisions, wavering edges, and regions where the brightness changes subtly. The A ring is like a carefully woven fabric with threads that vary in density and spacing, and it rewards close attention with its complexity. The C ring lies closer to Saturn than the B ring, and it's more translucent. If the B ring is like a thick curtain, the C ring is more like a veil, a region where the particles are spread out enough that you can see through them a little bit. The C ring doesn't catch as much light, and it has a softer, more subdued appearance. It blends quietly into the background, and you have to look carefully to see its edges and structure. Between the A ring and the B ring, there's a famous wide gap called the Cassini division. It's named after the astronomer Giovanni Domenico Cassini, who observed it in the 17th century. The Cassini division looks like a dark band separating the two bright rings, and for a long time people thought it might be completely empty, a true gap in the ring system. But despite its name, the Cassini division is not completely empty. There is still material in it, though the particles are much more sparse than in the bright rings on either side. It's a region where the density drops off sharply, creating a noticeable dark line when viewed from a distance, but up close, you'd still find ice and dust drifting through that space. There are also fainter rings closer in, including the D ring, which lies between the C ring and Saturn's cloud tops. The D ring is extremely faint and difficult to see, a ghostly presence that only becomes visible under certain conditions. Farther out, Saturn has a thin, narrow F ring that looks like a delicate strand, almost like a thread pulled tight around the outer edge of the main rings. The F-ring is one of the most intriguing parts of the ring system because it doesn't behave the way you might expect a simple ring to behave. It has kinks and braids, regions where it looks twisted or clumped, and it changes over time in ways that suggest it's actively being shaped by forces we'll explore in a moment. Saturn also has broader, fainter rings like the E-ring, which is linked to material from a moon. The E-ring is much more spread out than the main rings, and it's made of very fine particles that scatter light in a different way. It forms a kind of soft halo far from Saturn, a region where the ring system becomes less a disk and more a diffuse cloud. The rings form a layered system, like shelves of softly separated brightness, each one distinct but part of the same gentle architecture. Now that the map feels familiar, we can explore what the rings are made of. Tiny pieces, each following simple rules. Many ring particles are mostly water ice, which makes the rings bright and reflective. Water ice is one of the most common materials in the outer solar system, and it's particularly good at bouncing sunlight back toward the observer. That's why the rings can look so brilliant, even though they're made of small fragments, rather than one solid surface. The ice in the rings can be relatively clean in many places, which helps sunlight bounce back toward us without being absorbed or scattered away. But the ice isn't always pure. Some particles contain dust or rocky material mixed in with the ice, and these impurities can change the way a particle reflects light, making some regions of the rings slightly darker or more reddish in colour. Ring particles can collide gently, like slow-moving snowballs in orbit, because the particles are travelling at similar speeds and mostly in the same direction. Their collisions tend to be soft rather than violent. When two particles bump into each other, they might bounce apart, or they might stick together for a little while before separating again. These collisions tend to keep the particles from clumping into one big object. If the particles were left entirely alone, gravity might slowly pull them together, but the constant gentle bumping breaks up any clumps that start to form and keeps the ring material distributed. Each particle follows an orbit, but small nudges from collisions can change a particle's path slightly. A collision might slow a particle down a little, or speed it up, or push it slightly inward or outward. These changes are small, but over time they add up, and they contribute to the way the rings spread out and maintain their structure. The rings behave like a granular disk, meaning a system of many small pieces moving together. It's a bit like sand flowing through a funnel, or grains of rice settling in a jar. Each individual piece follows its own path, but the overall behaviour of the system is smooth and predictable. The system can form ripples and waves, even though it's made of separate particles. This might seem surprising at first. How can a collection of independent pieces create patterns that look like waves? The answer has to do with the way gravity and motion interact. When a disturbance travels through the ring system, perhaps caused by a moon passing nearby, or by the gravitational pull of Saturn itself, the particles respond by shifting their positions slightly. Some particles move a little closer together, while others spread out, and the result is a ripple that travels through the ring like a wave moving across the surface of a pond. The rings can have different particle sizes in different regions, and this variation adds another layer of texture to the system. Some regions might be dominated by small grains, while others contain more large boulders, and the mix of sizes affects how the ring looks and how it behaves. In a soothing way, the rings show how complexity can emerge from simple pieces repeating simple motion. Each particle is just orbiting Saturn, following the basic rules of gravity and motion, but when you put billions of particles together, all orbiting at slightly different speeds and distances, you get a system that's rich in detail and beauty. The rings don't need a central plan or a guiding hand to create their structure. They just need the steady pull of gravity and the patient repetition of orbital motion, and the patterns emerge naturally, like frost forming on a window or sand settling into ripples on a beach. With the particles in mind, let's let gravity do its quiet work and see why the rings stay spread out instead of forming a single moon. Ring particles orbit Saturn at different speeds depending on their distance from the planet. Particles close to Saturn orbit faster than particles farther away. This is a fundamental rule of orbital mechanics, related to the way gravity gets stronger as you get closer to a massive object. If you're orbiting close to Saturn, you feel a stronger pull, and you have to move faster to maintain your orbit. If you're farther out, the pull is weaker, and you can move more slowly and still stay in a stable path. This difference in speed is called differential rotation, and it helps stretch structures into long bands. Imagine you have a row of particles lined up side by side, all at slightly different distances from Saturn. The inner particle is moving faster, the outer particle is moving slower, and the middle particle is somewhere in between. As time goes by, the faster particle pulls ahead and the slower particle falls behind, and the row stretches out into a long, thin line. This is what happens to the rings. Any clump or cluster of particles gets stretched by differential rotation, and over time the clumps turn into streamers and bands. It's a gentle process, but it's relentless, and it's one of the reasons the rings look the way they do. Saturn's gravity pulls particles inward, while their orbital motion keeps them from falling straight down. This is the essence of an orbit. If you drop a particle straight towards Saturn with no sideways motion, it would fall directly down and eventually crash into the planet. But if you give the particle some sideways motion, some velocity perpendicular to the direction of Saturn's gravity, then the particle will curve around the planet instead of falling straight in. The pull of gravity keeps bending the particle's path, and the particle keeps moving sideways, and the result is an orbit. The balance between gravity and sideways motion is what makes an orbit stable. The particle is constantly falling towards Saturn, but it's also constantly missing Saturn because of its sideways speed, and the two motions balance out into a circular or elliptical path. Inside a certain region, tidal forces can make it hard for large objects to form and stay intact. This region is related to the idea of the Roche limit, which is a concept that helps explain why Saturn has rings in the first place. The Roche limit is the distance from a planet inside which the planet's gravity is strong enough to pull apart a large object that's held together only by its own gravity. Imagine a small moon made of rubble and ice, orbiting Saturn. If the moon is far enough away, it can hold itself together just fine. But if it drifts too close to Saturn, the side of the moon facing the planet feels a stronger pull than the side facing away, and this difference in pull, the tidal force, starts to stretch the moon. If the tidal force is strong enough, it can overcome the moon's own gravity and pull the moon apart into pieces. Those pieces then continue to orbit Saturn, and they become part of the ring system. Collisions between particles also break up larger clumps and keep the ring material distributed. Even if a few particles do stick together and start to form a small moonlet, the moonlet is likely to get hit by another particle sooner or later, and the collision can break it apart again. The result is a broad, thin disk rather than a single solid ring. The particles are spread out over a huge area, and they're all moving in nearly the same plane, which keeps the disk thin. The rings can feel like a calm demonstration of balance, pull and motion held in steady harmony. Gravity pulls inward, motion carries sideways, and the two forces work together to create a stable, lasting structure that can persist for millions of years. Now we can glide over the ring surface and notice the beautiful patterns, gaps, divisions, and narrow lanes etched by gentle forces. The Cassini division, which we mentioned earlier, is shaped in part by gravitational resonances with Saturn's moons. A resonance happens when orbital periods form a simple ratio, creating repeating nudges. For example, imagine a ring particle that orbits Saturn exactly twice for every one orbit of a nearby moon. Every time the moon completes one orbit, the ring particle is in the same position relative to the moon, and the moon's gravity gives the particle a little tug. This tug happens over and over again, always in the same place in the particle's orbit, and the repeated nudges add up over time. Eventually the particle's orbit gets changed, it might get pushed inward or outward, or its orbit might become more elliptical, and the result is that the particle is no longer in that region. Over millions of years, these resonances can clear out entire sections of the ring, creating gaps and divisions. These repeating nudges can clear out some regions and sharpen boundaries. The edges of the Cassini division, for instance, are quite sharp when you look at them closely. The division isn't just a gradual thinning of particles, it's a relatively abrupt drop in density, and that sharpness comes from the way resonances sweep particles out of certain zones. The A-ring contains the Encke gap, a narrow gap with a moon inside it. The small moon Pan orbits within the Encke gap and helps maintain its structure. Pan is only about 28 kilometers across, but it's large enough to have a noticeable gravitational effect on the ring particles around it. As Pan orbits, it sweeps up particles in its path and pushes others out of the way, and the result is a clear gap where the moon travels. The Keeler gap is another narrow gap near the outer edge of the A-ring. The moon Daphnis orbits in the Keeler gap and can create wavy edges along the gap. Daphnis is even smaller than Pan, only about 8 kilometers across, but it's enough to disturb the particles at the edges of the gap. When Daphnis passes by, its gravity pulls on the nearby particles, and the edges of the gap develop little waves, like ripples in water. These waves are visible in high-resolution images, and they show how even a very small moon can have a noticeable effect on the ring structure. Spiral density waves appear in rings as tightly wound ripples caused by resonances. These waves are one of the most beautiful and intricate features of Saturn's rings. They look like closely spaced lines or bands that spiral outward from a central point, and they form when a resonance causes particles to bunch up in certain regions and spread out in others. The waves are a bit like the grooves on a vinyl record, or like the ripples you see when you drop a stone into a still pond. They're a visual record of the gravitational interaction between the rings and the moons, a kind of pattern that the rings remember and display. Bending waves can also occur, where ring material is tilted slightly up and down like a slow, soft swell. Instead of changing the density of particles in the ring plane, bending waves change the vertical position of the particles, so parts of the ring rise a little above the main plane and other parts dip a little below. These waves can be caused by resonances or by interactions with moons that have inclined orbits. They add another layer of structure to the rings, and they show how the ring system can respond to forces in 3 dimensions, not just in the flat plane of the disk. These patterns are like the rings recording gentle gravitational music in visible lines. Every gap, every wave, every division is a trace of the way gravity has shaped the system over time. The rings don't just sit there unchanged, they respond to the moons and to Saturn itself, and they create patterns that reflect those interactions. It's a kind of slow, patient artistry, where the medium is ice and dust and the tools are gravity and motion, and the result is a structure of astonishing beauty and complexity. From those etched patterns, we can float outward to the thinnest, most delicate strand, the F-ring and its quiet guardians. The F-ring is a narrow ring just outside the main bright rings, and it's one of the most dynamic and changeable parts of the ring system. It often looks braided or kinked, like a thread that has been lightly twisted. Sometimes the F-ring appears as a single strand, and sometimes it looks like multiple strands woven together. The structure changes over time, and images taken years apart can show significant differences in the way the ring looks. The F-ring is shaped by nearby moons called shepherd moons. 2 famous shepherd moons are Prometheus and Pandora, and they orbit on either side of the F-ring. Their gravity helps confine the ring and sculpt its edges. Prometheus orbits just inside the F-ring, and Pandora orbits just outside it, and together they act like shepherds guiding a flock. Their gravitational pulls keep the ring particles from drifting too far inward or outward, and they maintain the narrow structure of the ring. Prometheus can create streamers and clumps by pulling on ring material during close passes. Because Prometheus's orbit is slightly elliptical, it doesn't always stay at the same distance from the F-ring. Sometimes it gets closer, and when it does, its gravity pulls more strongly on the ring particles, creating disturbances that show up as streamers or channels in the ring. These disturbances are temporary, they fade and change as the particles continue to orbit, but they're visible in high-resolution images, and they show how active the F-ring is. The F-ring can contain small, temporary clumps that form and disperse over time. Some of these clumps may be short-lived moonlets that start to gather and then break apart. A moonlet might form when a few particles stick together, but if it's in a region where collisions are common, it won't last long. The constant jostling and nudging from other particles combined with the gravitational effects of Prometheus and Pandora means that the F-ring is always changing, always reshaping itself. The F-ring shows how a very thin structure can still be lively and detailed. Even though it's only a few kilometers wide, much narrower than the main rings, it has more variation and complexity than you might expect. It's a gentle reminder that even the finest lines in nature can be held steady by quiet, repeated pulls. The shepherd moons don't have to be large or dramatic to have an effect. They just have to be there, orbiting patiently, tugging on the ring particles over and over again, and the structure emerges from that steady interaction. Now we'll drift farther into the faint outer rings, where the glow becomes softer and the ring material becomes more spread out and airy. The E-ring is much broader and fainter than the main rings. It extends over a huge distance, from well inside the orbit of the Moon, Mimas all the way out past the orbit of Dione. The E-ring is made largely of very tiny icy particles, more like mist than pebbles. These particles are so small that they scatter light in a different way than the larger particles in the main rings. Instead of reflecting light back in a bright concentrated beam, the tiny particles scatter light in all directions, creating a soft, diffuse glow. The E-ring is strongly linked to Saturn's moon Enceladus, which is one of the most fascinating moons in the entire solar system. Enceladus has geyser-like plumes that release water ice into space. These plumes shoot out from cracks in the moon's icy surface, and they send tiny ice crystals flying outward at high speed. Some of that released ice becomes part of the E-ring. The plumes are powered by heat from inside Enceladus, possibly from tidal heating caused by the gravitational pull of Saturn and other moons. The fact that Enceladus is geologically active with liquid water beneath its icy crust makes it one of the most exciting places to study in the search for conditions that might support life. Because the particles in the E-ring are small, sunlight can scatter through them in a gentle haze. The E-ring doesn't have the sharp boundaries or the bright defined appearance of the main rings. Instead, it's more like a cloud, a region where the density of particles gradually increases and then gradually decreases again. If the main rings are like shining shelves, these fainter rings are like a thin fog of ice drifting quietly outward. Saturn also has a faint G-ring, which contains an arc of brighter material. The G-ring lies between the orbits of Mimas and Enceladus, and it's made of very fine dust. The arc is a region where the dust is slightly more concentrated, and it shows up as a brighter patch in images. The G-ring is thought to be maintained by small moonlets, or by dust kicked up from larger objects by micrometeorite impacts. It's another example of how the ring system has layers of structure at different scales, from the bright main rings down to these faint, dusty halos. Some faint rings can be influenced by dust and small particles interacting with Saturn's magnetic environment. Saturn, like Earth, has a magnetic field, and charged particles can become trapped in this field and move along the field lines. Dust grains can pick up electric charges from sunlight or from interactions with other charged particles, and once charged, they can be affected by the magnetic field. This interaction can help maintain some of the faint rings, or it can cause particles to spiral inward or outward over time. The ring system includes both bright bands and soft clouds of material, and each region has its own story of how it formed and how it's maintained. With those soft outer structures in view, we can talk about where the rings might have come from, several calm possibilities still being studied. Scientists are still studying the exact origin of Saturn's rings, and there isn't one single answer that everyone agrees on. Instead, there are several possibilities, each supported by different lines of evidence, and the truth might involve a combination of these ideas. One possibility is that the rings formed from a moon or icy body that broke apart. If a small moon wandered too close to Saturn, tidal forces could have pulled it apart, and the fragments could have spread out into a ring. Alternatively, a moon might have been shattered by a collision with a comet or asteroid, and the debris could have formed the ring system. Another possibility is that ring material formed early in Saturn's history and evolved over time. According to this idea, the rings might have been present since shortly after Saturn itself formed, or they might have formed from material left over from the planet's formation. Over billions of years, the rings would have changed as particles collided, as material was added by impacts from comets, and as some material was lost to Saturn's atmosphere or to moons sweeping through the rings. Impacts from comets or small bodies could contribute material or reshape existing rings. The outer solar system is full of small icy objects, comets, asteroids, and chunks of debris, and these objects occasionally collide with Saturn's moons or with the rings themselves. Each collision can add new material to the ring system, or it can break up existing particles into smaller pieces. Over long timescales, these impacts can have a significant effect on the composition and structure of the rings. If a moon came too close to Saturn, tidal forces could have helped pull it apart. This is the Roche limit scenario we mentioned earlier, and it's one of the leading ideas for how the rings might have formed. The key point is that the moon doesn't have to be very large. Even a relatively small moon, if it's made of loosely bound material, can be torn apart by tidal forces if it gets close enough to Saturn. Once the moon breaks up, the pieces continue to orbit, and they gradually spread out into a disk. Collisions among ring particles can grind material down into smaller pieces over long periods. This process is called collisional erosion, and it's one of the reasons the rings are made of such a variety of particle sizes. When two particles collide, they can chip pieces off each other, and those chips become smaller particles. Over millions or billions of years, this grinding can turn large boulders into pebbles, and pebbles into dust. The process also tends to smooth out the surfaces of the particles, which might contribute to the brightness of the rings. The brightness of the rings suggests a large amount of relatively clean ice in many regions. This is one of the clues that scientists use to think about the age of the rings. If the rings were very old, billions of years old, you might expect them to have accumulated more dust and darkened over time. The fact that they're so bright suggests that either the rings are relatively young, or there's some process that keeps them clean, such as particles sticking together and then being removed by sweeps from moons or by falling into Saturn. Some research discusses whether the rings are young or old, and the debate continues as measurements improve. Recent data from the Cassini mission, which ended in 2017, suggested that the rings might be younger than previously thought, perhaps only a few 100 million years old rather than billions of years old. This estimate comes from measuring the rate at which material is falling from the rings into Saturn's atmosphere, and from studying the mass of the rings. But the question is still open, and different methods give different answers, so scientists continue to refine their models and gather more data. Even without a final answer, the ring system is clearly dynamic, changing slowly like a long, quiet weather pattern. The rings are not frozen in time, they're evolving, responding to the forces acting on them, and they'll continue to change in the future. It can be soothing to let the origin remain a gentle mystery for now, like a story with multiple calm chapters. The rings are there, they're beautiful, and they're telling us something about the history of Saturn and the solar system, even if we haven't decoded every detail yet. Now we'll visit the explorers that helped us see the rings clearly, spacecraft and telescopes that turned distant light into detailed understanding. Early astronomers noticed Saturn's strange shape before understanding it had rings. When Galileo Galilei first observed Saturn through his small telescope in the early 17th century, he saw something odd on either side of the planet, but his telescope wasn't powerful enough to show what it was. He described Saturn as having ears, or handles, and he didn't know what to make of the observation. A few years later, the rings appeared to vanish. This was when Saturn's rings were oriented edge-on as seen from Earth, and Galileo was confused about what had happened. Better telescopes eventually revealed the rings more clearly as separate from the planet. In the mid-17th century, the Dutch astronomer Christian Huygens used an improved telescope to observe Saturn, and he was the first to correctly describe the rings as a flat disk surrounding the planet. Later, Cassini observed the gap that now bears his name, and other astronomers continued to study the rings, mapping their structure and measuring their properties with ever-improving instruments. The spacecraft Voyager 1 and Voyager 2 provided major close-up images and measurements. These two spacecraft flew past Saturn in 1980 and 1981, and they sent back images that showed the rings in unprecedented detail. The Voyager images revealed that the rings were much more complex than anyone had thought. What had looked like a few broad bands from Earth turned out to be made up of thousands of narrow ringlets, and the images showed gaps, waves, and fine structures that had never been seen before. The Voyager missions also measured the temperature of the rings, the composition of the particles, and the way the rings interacted with Saturn's magnetic field. The mission Cassini spent many years studying Saturn and its rings in detail. Cassini was launched in 1997, arrived at Saturn in 2004, and orbited the planet for 13 years before its mission ended in 2017. During that time, Cassini made hundreds of orbits, observing the rings from every angle and at every distance. Cassini observed ring structure, waves, and fine gaps with remarkable clarity. The spacecraft used multiple instruments to study the rings, cameras to take visible light images, spectrometers to measure the composition of the particles, and radio instruments to probe the rings' density and structure. Scientists study rings by measuring how they reflect sunlight at different wavelengths. Different materials reflect light in different ways, and by breaking the light into a spectrum, like a rainbow, scientists can identify the substances present in the ring particles. For example, water ice has a distinctive signature in the infrared part of the spectrum, and by measuring the strength of this signature, scientists can estimate how much ice is in the rings and how pure it is. They also study rings using radio signals sent through the rings to see how the signal changes. This technique is called radio occultation, and it works a bit like shining a flashlight through a fog. When Cassini passed behind the rings as seen from Earth, it sent a radio signal back to Earth, and that signal had to travel through the rings to reach us. By measuring how the signal was weakened or scattered by the ring particles, scientists could calculate the density of particles in different regions and learn about the size distribution of the particles. When a star passes behind the rings, the way its light dims can reveal ring density and structure. This technique is called stellar occultation, and it's similar to radio occultation but uses starlight instead of radio waves. As a star moves behind the ring particles block some of the starlight, and the amount of dimming tells you how dense the particles are in that part of the ring. By watching many stars pass behind different parts of the rings, scientists can build up a detailed map of the ring structure. These methods are like gentle shadow readings, turning faint changes into information. They don't require physically touching the rings or disturbing them in any way. Instead, they use light and radio waves, things that pass through the rings naturally, and they extract information from the subtle ways those signals are changed. The more we observe, the more the rings feel like a living system, quietly patterned and carefully measurable. Every new observation adds another piece to the puzzle, and the picture becomes clearer and richer. Let's pause for a moment and think about what it means for the rings to be so thin. When we say the rings are thin, we're talking about a dimension that's almost impossible to comprehend at first. The rings stretch out across a distance of more than 280,000 kilometers from their inner edge to their outer edge. But in many places they're only 10 to 30 meters thick. That's like comparing the width of a football field to the thickness of a sheet of aluminum foil. It's a ratio that's hard to hold in your mind, but it's important because it tells us something fundamental about how the rings behave. The thinness comes from the way the particles move. They're not moving randomly in all directions. They're mostly moving in the same plane, like cars on a very wide highway. When particles collide, they can bounce up or down a little bit, but those vertical motions tend to average out over time. If a particle gets knocked upward, it will eventually fall back down due to Saturn's gravity, and if it gets knocked downward, it will bounce back up. The net result is that the particles settle into a flat disk, and the disk stays flat because the particles keep bumping into each other and evening out their vertical motions. This process is a bit like what happens when you shake a box of cereal. If you shake it gently, the pieces inside settle into a more compact arrangement, and the box becomes flatter as the empty space gets squeezed out. The ring particles are doing something similar, except instead of being shaken by hand, they're being jostled by collisions, and instead of settling into a box, they're settling into a thin disk around Saturn. It's a slow, patient process, but it's very effective, and it's why the rings have such a dramatic aspect ratio. The thinness also affects the way we see the rings. When the rings are tilted toward us, we see them as wide, bright bands, and we can see all the structure and detail in the ring system. But when the rings are edge-on, they become almost invisible, and Saturn looks like a plain sphere with no rings at all. This happens roughly every 15 years, because Saturn takes about 29.5 years to orbit the Sun, and during that time the rings go through two periods when they're edge-on as seen from Earth. These edge-on periods are actually useful for scientists, because they make it easier to see faint moons and structures that would normally be hidden by the brightness of the rings. Now let's think more carefully about the particles themselves and what they're like up close. If you could somehow visit the rings and float among the particles, you'd find yourself in a strange and beautiful environment. The particles would be all around you, drifting past in their orbits, each one moving at a slightly different speed. Some would be tumbling slowly, reflecting sunlight as they turned, and others would be moving smoothly along their paths. The space between particles would be mostly empty. The rings look solid from a distance, but up close there's a lot of empty space. The particles would vary in size, shape, and brightness. Some would be almost perfectly spherical, smoothed by countless, gentle collisions over millions of years. Others would be irregular and jagged, perhaps freshly broken from a larger object. Some particles would be bright white, made of clean water ice that reflects sunlight efficiently. Others would be darker, with dust or rocky material mixed in, and they might have a greyish or brownish tint. The variety would be endless, and no two particles would be exactly alike. If you reached out and touched one of the particles, you'd find that it's cold, extremely cold. The temperature in the rings is far below freezing. typically around minus 180 degrees Celsius or even colder. At that temperature, water ice is as hard as rock, and the particles would feel solid and firm. The surface might be smooth in some places and rough in others, depending on the particle's history. Some particles might have small craters from impacts with tiny grains of dust, while others might be covered in a fine layer of frost. The particles would also be moving at different speeds depending on where they are in the ring system. In the inner parts of the rings, close to Saturn, the particles orbit faster, completing a trip around the planet in just a few hours. In the outer parts of the rings, the particles move more slowly, taking longer to complete each orbit. If you were floating in the middle of the A-ring, for example, the particles around you would be moving at about 20 kilometers per second, fast enough to cross a city in the blink of an eye. But because all the particles are moving in the same direction at similar speeds, the relative motion between neighbouring particles is much slower, just a few centimeters per second in many cases. It's this slow relative motion that makes the collisions gentle rather than destructive. The lighting in the rings would be remarkable. Sunlight would stream in from one direction, illuminating the particles and making them glow. But the light wouldn't be harsh or direct. It would be softened by the scattering from countless particles, creating a kind of diffuse glow that fills the space. Some particles would be in shadow, blocked from direct sunlight by other particles, and they would appear darker and more subdued. The contrast between the bright sunlit particles and the shadowed ones would create a sense of depth and dimension, and you'd be able to see the three-dimensional structure of the ring system in a way that's not possible from a distance. You might also see some particles that are backlit by sunlight, with light streaming through gaps and creating halos and glows. This kind of lighting can reveal very fine dust that's invisible under normal conditions, and it can make the rings look even more ethereal and delicate. The Cassini spacecraft captured images of the rings in this backlit geometry, and the results were stunning. The rings looked like gossamer threads and veils, with light shining through them and revealing structures that had never been seen before. Now let's consider the forces that shape the rings on larger scales. We've talked about gravity and collisions, but there are other factors at play as well. One of these is radiation pressure from sunlight. When sunlight hits a particle, it exerts a tiny push on the particle, just like the wind pushing on a sail. For large particles, this push is negligible, but for very small particles, grains of dust just a few micrometers across, the radiation pressure can be significant. It can push these tiny particles outward, away from the sun, and over time it can cause them to drift out of the ring system entirely. This effect helps explain why the rings don't have more dust than they do. If the rings were constantly grinding down particles into smaller and smaller pieces, you might expect the rings to become filled with dust over time, but the radiation pressure acts like a filter, removing the tiniest particles and leaving behind the larger ones. This helps keep the rings relatively clean, and prevents them from becoming a thick, dusty haze. Another force that affects the rings is the solar wind, which is a stream of charged particles flowing out from the sun. The solar wind interacts with Saturn's magnetic field, creating a complex environment around the planet. Some ring particles can become electrically charged by sunlight or by interactions with the solar wind, and once charged, they can be affected by Saturn's magnetic field. This interaction is most important for the faint, dusty rings, where the particles are small enough to be easily influenced by electromagnetic forces. Saturn's magnetic field itself is an important part of the environment around the rings. The field is generated deep inside Saturn, where electrically conducting materials flow and create electric currents. These currents produce a magnetic field that extends far out into space, surrounding the planet and its rings. The field isn't perfectly symmetrical. It has a complex structure with regions where the field is stronger or weaker, and it changes over time in response to conditions inside Saturn and in the surrounding space. Charged particles from the solar wind and from Saturn's moons can become trapped in the magnetic field, spiraling along the field lines and bouncing back and forth between the planet's poles. These trapped particles form radiation belts, similar to Earth's Van Allen belts, and they create a hazardous environment for spacecraft. The Cassini mission had to navigate through these radiation belts carefully, and the spacecraft was designed to withstand high levels of radiation during its close approaches to Saturn. The interaction between the rings and the magnetic field is subtle but important. In some regions, the rings can actually absorb charged particles from the radiation belts, creating gaps or depressions in the particle population. These gaps can be detected by instruments that measure the intensity of radiation, and they provide a way to map the structure of the rings from the pattern of particle absorption. It's another example of how the rings affect their environment, not just through gravity but through electromagnetic interactions as well. Now let's think about how the rings change over time. We tend to think of the rings as permanent features, something that's always been there and always will be, but the reality is more complex. The rings are dynamic, evolving structures, and they're changing on timescales ranging from hours to billions of years. On short timescales, the rings respond to the gravitational tugs of passing moons, creating waves and disturbances that ripple through the system. These changes happen relatively quickly, and they can be observed by spacecraft over the course of days or weeks. On longer timescales, the rings evolve as particles collide and grind each other down, as material is added by impacts from comets and meteoroids, and as some material is lost to Saturn's atmosphere or to escaping moons. The Cassini mission provided some of the best evidence for how fast these processes are happening. One of Cassini's most important discoveries was the detection of material falling from the rings into Saturn's atmosphere. This material, which is mostly water ice mixed with some organic compounds and silicates, rains down on Saturn at a rate of thousands of kilograms per second. That might not sound like much compared to the total mass of the rings, but over time it adds up. If you extrapolate this loss rate backward in time, you can estimate how long the rings could have been losing material at this rate before they would have been depleted. The answer is surprising, only a few 100 million years, which is much shorter than the age of Saturn itself. This suggests that either the rings are relatively young, perhaps formed a few 100 million years ago from the breakup of a moon or a large comet, or there's some process that's replenishing the ring material and keeping the rings from disappearing entirely. The idea that the rings might be young is controversial, and it's still being debated by scientists. If the rings are young, it raises the question of why they formed when they did. Was there a specific event that triggered their formation, or is it just a coincidence that we happen to be living at a time when Saturn has rings? On the other hand, if the rings are old, then there must be some mechanism that's keeping them from fading away, and scientists are working to understand what that mechanism might be. One possibility is that the rings are being replenished by material from Saturn's moons. When a small meteoroid hits one of the moons, it can kick up a cloud of ice and dust, and some of that material can escape from the moon and become part of the ring system. This process is particularly effective for moons with weak gravity, where it doesn't take much energy to launch material into space. Over time, this steady trickle of material could balance out, the loss from the rings falling into Saturn, keeping the total mass of the rings roughly constant. Another possibility is that the rings are recycling material internally. Maybe particles that fall towards Saturn don't all make it all the way into the atmosphere. Maybe some of them get scattered by interactions with the magnetic field or with other particles, and they end up back in the rings. Or maybe there are processes that concentrate material in certain regions of the rings, creating temporary reservoirs that can later be redistributed. These are active areas of research, and scientists are using the data from Cassini to test different models and figure out which scenarios are most consistent with the observations. The age question is intimately tied to the composition of the rings. If the rings are mostly clean water ice, as the observations suggest, then how did they stay so clean over billions of years? One idea is that the rings have a kind of self-cleaning mechanism. When particles collide, they can break off small chips and fragments, and these fragments might carry away impurities, leaving behind cleaner ice. Or maybe the impurities tend to concentrate in certain particles, which then fall into Saturn more quickly, again leaving behind cleaner ice in the rings. It's also possible that there's ongoing bombardment by small icy comets that add fresh water ice to the rings and help maintain their brightness. The colour of the rings provides another clue about their composition and history. While the rings are mostly bright and white, they do have some variation in colour. Some regions are slightly more reddish, which might indicate the presence of organic compounds or iron-bearing minerals. These redder regions could be areas where impurities are more concentrated, or they could be places where the ice has been exposed to more radiation and has undergone chemical changes. By mapping the colour variations across the rings, scientists can learn about the distribution of different materials and about the processes that affect the ring particles. Now let's turn our attention to the way the rings interact with Saturn's atmosphere. The material falling from the rings doesn't just vanish when it reaches the planet. It has to go somewhere, and that somewhere is the upper atmosphere of Saturn. When the ring particles enter the atmosphere, they heat up due to friction with the atmospheric gases, and they vaporize, releasing water vapor, silicates, and organic compounds into the air. This material then mixes with the existing atmosphere and can affect its chemistry and structure. One of the effects of this ring rain is to change the composition of Saturn's upper atmosphere in certain regions. The material tends to fall near the planet's equator, because that's where the rings are, and it creates a kind of equatorial band where the atmosphere has more water and other ring-derived materials than it would otherwise. This can affect the temperature and density of the atmosphere in those regions, and it might even influence the formation of clouds and hazes. The ring rain also has implications for understanding Saturn's interior and evolution. The fact that material is constantly falling into the planet means that Saturn is gradually accreting mass from its rings, albeit at a very slow rate. Over the age of the solar system, this could add up to a significant amount of material, and it could affect the planet's overall composition and structure. It's another reminder that the rings and the planet are not separate systems. They're intimately connected, constantly exchanging material and energy. Another fascinating aspect of the rings is the way they create their own environment through electromagnetic effects. We mentioned earlier that charged particles can interact with Saturn's magnetic field, but there's more to the story. The rings themselves can become electrically charged through a process called photoelectric emission. When sunlight hits the surface of a ring particle, it can knock electrons out of the surface, leaving the particle with a positive charge. These free electrons then move through space, creating a population of charged particles around the rings. This charging process can have several effects. For one thing, it can cause particles to repel each other electrostatically, which might affect the spacing and arrangement of particles in the rings. It can also create electric fields that accelerate charged particles, sending them spiraling along magnetic field lines. And it can lead to the formation of plasma clouds and sheaths around the rings, where the density of charged particles is higher than in the surrounding space. The Cassini spacecraft carried instruments that could detect these charged particles and measure the electric and magnetic fields around the rings. The data revealed a complex and dynamic environment, with waves and disturbances propagating through the plasma, with electric currents flowing along the magnetic field lines, and with particles being accelerated and decelerated in response to changing conditions. It's a reminder that the rings are not just passive collections of ice and rock, they're active participants in the electromagnetic environment of the Saturn system. Let's shift now to thinking about the rings in the context of the broader solar system. Saturn's rings are unique in their size and brightness, but the basic physics that governs them applies to other ring systems as well. Jupiter, Uranus and Neptune all have rings, and while these rings are much fainter and less extensive than Saturn's, they're governed by the same principles of gravity, orbital mechanics, and particle interactions. Jupiter's rings, for example, are made mostly of very fine dust, probably kicked up from the planet's small inner moons by micrometeorite impacts. The rings are faint and difficult to see, but they were discovered by the Voyager spacecraft in 1979, and they've been studied in more detail by subsequent missions. The rings have several components, including a thin main ring and a broader, fainter halo ring that extends inward toward the planet. The structure of Jupiter's rings is shaped by the same kinds of resonances and gravitational interactions that affect Saturn's rings, but the outcome is different because the source material and the environment are different. Uranus has a system of narrow rings that are quite different from Saturn's broad, bright rings. Uranus's rings are dark, much darker than Saturn's, and they're composed of particles that are larger on average, more like gravel than like dust. The rings are confined to narrow bands, separated by wide gaps, and they're maintained by the gravitational influence of small shepherd moons. The ring system was discovered in 1977, when Uranus passed in front of a star, and observers noticed that the star's light dimmed several times before and after the planet blocked, it indicating the presence of rings. Neptune's rings are similar to Uranus's in some ways, but they have one unique feature. They contain arcs, or regions where the ring material is clumped together instead of being spread evenly around the planet. These arcs are thought to be maintained by resonances with Neptune's moon Galatea, which nudges the particles and keeps them from spreading out. The arcs are a beautiful example of how subtle gravitational effects can create structure in ring systems, and they show that there's still a lot we don't understand about how rings behave. Beyond the giant planets, there are even ring systems around smaller bodies in the solar system. The asteroid Chariklo, for instance, was discovered to have 2 narrow rings when it passed in front of a star in 2013. This was a complete surprise because no one expected an object as small as Chariklo, it's only about 250 kilometers across, to have rings. The discovery showed that rings might be more common than we thought, and that they can form around bodies of very different sizes and types. All of these ring systems teach us something about the processes that shape planetary environments. They show us how particles interact under gravity, how moons can sculpt and maintain structures, and how impacts and collisions can create and destroy material. They also give us a window into the early solar system, when planets were still forming and the space around them was filled with debris and leftover material. Studying rings today helps us understand what conditions were like billions of years ago, and how the solar system evolved into the configuration we see today. Let's return to Saturn and think about what the rings look like at different times and from different perspectives. The appearance of the rings changes dramatically depending on the angle from which they're viewed and the lighting conditions. When the sun is behind the observer, the rings are brightly lit and show their full glory, with all the structure and detail visible. This is called the lit face of the rings, and it's the view we're most familiar with from images taken by spacecraft and telescopes. But when the sun is on the opposite side of the rings from the observer, the rings are backlit, and they look completely different. In this geometry, the light has to pass through the rings to reach the observer, and the amount of light that gets through depends on how transparent the rings are. The densest parts of the rings block most of the light, appearing dark, while the more transparent regions let more light through, appearing brighter. This backlit view can reveal structures that are invisible in normal lighting, such as very fine dust and tenuous ringlets. The Cassini spacecraft took advantage of this by observing the rings in both lit and backlit geometries, and by comparing the two views, scientists were able to learn a lot about the distribution of particle sizes and the density of the rings. The backlit images were particularly useful for studying the faint rings, like the E ring and the G ring, because these rings are much more visible when backlit than when lit from the front. The rings also change in appearance as Saturn moves through its orbit around the Sun. Because Saturn's rotational axis is tilted relative to its orbital plane, the angle at which sunlight hits the rings changes over the course of Saturn's year. At some times the Sun is high above the rings, shining down on the northern face, and at other times the Sun is below the rings, shining up on the southern face. And twice during each orbit the Sun passes through the plane of the rings, creating a period called Saturn's equinox. During equinox, the Sun shines edge onto the rings, illuminating them in a very thin band and casting long shadows from any particles or structures that stick up above the ring plane. This is an ideal time to look for small moons and moonlets embedded in the rings because their shadows can be much larger and more visible than the moons themselves. Cassini observed Saturn's equinox in 2009, and the images revealed several previously unknown moonlets and showed features in the rings that had never been seen before. The changing seasons on Saturn also affect the rings in more subtle ways. The temperature of the ring particles varies depending on how much sunlight they receive, and this can affect the physical properties of the ice. When the particles are warmer, the ice can be slightly softer and more prone to sticking together during collisions. When the particles are colder, the ice is harder and more brittle. These differences are small, but over long timescales they might affect the evolution and structure of the rings. Now let's think about what it would be like to observe the rings from the surface of Saturn if Saturn had a solid surface to stand on. Of course, Saturn is a gas giant with no solid surface in the way we usually think of it, but we can imagine what the view would be like from deep in the atmosphere, looking up at the rings overhead. From the equator of Saturn, the rings would appear as a thin, bright line stretching across the sky from horizon to horizon, directly overhead. The line would be incredibly narrow, because you'd be looking at the rings edge-on, and they'd appear as a luminous thread dividing the sky in half. As you moved away from the equator, toward higher latitudes, the rings would appear to tilt and you'd start to see them at an angle. The farther north or south you went, the more of the ring plane would become visible, and the rings would appear wider and brighter. If you travelled all the way to Saturn's poles, you'd be looking down on the rings from above, and they'd appear as enormous circular disks surrounding the planet. But the most spectacular views would be from latitudes somewhere in between, where the rings would arch across the sky at a dramatic angle. From these vantages, the the rings would be a dominant feature of the sky, far more prominent than the moon appears from Earth. They'd cast shadows on the planet during the day, creating bands of darkness that would move across the surface as Saturn rotated, and at night the rings would reflect sunlight down onto the planet, creating a soft, diffuse illumination that would make the nighttime much brighter than it would otherwise be. Of course, this is all speculation, because we can't actually stand on Saturn's surface, but it's a useful thought experiment because it helps us appreciate the scale and beauty of the rings from a different perspective. The rings are not just something to look at from a distance. They're an integral part of Saturn's environment, affecting the planet's climate, its atmosphere, and even the appearance of its sky. Let's consider now the role that the rings play in Saturn's overall system of moons. Saturn has more than 80 known moons, ranging from tiny moonlets just a few kilometers across to giant Titan, which is larger than the planet Mercury. Many of these moons orbit outside the rings, but some orbit within or very close to the ring system, and these moons have a special relationship with the rings. We've already talked about shepherd moons like Prometheus and Pandora, which orbit on either side of the F-ring and help maintain its structure. There are other small moons embedded within the rings themselves, like Pan in the Encke Gap and Daphnis in the Keeler Gap. These moons are too small to be seen easily from Earth, but they were discovered by careful analysis of the structures they create in the rings. The gaps they carve out are much wider than the moons themselves because the moon's gravity affects particles over a large region. There are also larger moons that orbit just beyond the outer edge of the rings. These moons, like Mimas, Enceladus, and Tethys, interact with the rings through gravitational resonances. Even though they're far from the rings, their gravity can reach across the empty space and affect particles at specific distances where the orbital periods match up in simple ratios. These resonances are what create some of the gaps and divisions in the rings, like the Cassini division, which is partly cleared out by a resonance with Mimas. The relationship between the moons and the rings is a two-way street. The moons shape the rings, but the rings also affect the moons. When a moon passes close to the rings, the gravity of all those particles can tug on the moon, changing its orbit slightly. Over long timescales, these tugs can cause the moon's orbit to evolve, drifting inward or outward, becoming more or less eccentric. This orbital evolution is an important process in the Saturn system, and it helps explain the current configuration of moons and rings. Some scientists think that the rings might even be a source of new moons. If particles in the outer parts of the rings manage to clump together and stick, they could gradually build up into larger and larger objects, eventually forming moonlets and then full-sized moons. This process would take a very long time, but it's possible that some of Saturn's small moons formed this way, accreting from ring material over millions of years. On the other hand, moons can also be a source of ring material. If a moon wanders too close to Saturn and crosses the Roche limit, it can be torn apart by tidal forces, and the debris becomes part of the rings. Or if a moon is hit by a comet or asteroid, the impact can shatter the moon and spread fragments into orbit. These processes can create new rings, or add material to existing rings, and they show that the ring system is not static but constantly changing in response to the dynamics of the moon system. Now let's think about the future of Saturn's rings. What will happen to them over the next millions and billions of years? Will they persist, or will they gradually fade away? The answer depends on several factors, including the rate at which material is being lost from the rings, the rate at which new material is being added, and the processes that shape and maintain the ring structure. As we mentioned earlier, the Cassini mission found that material is falling from the rings into Saturn's atmosphere at a significant rate. If this rate continues unchanged, the rings could be depleted in a few 100 million years. But it's not clear whether the loss rate will stay constant. It might slow down as the rings become less dense, or it might speed up if the remaining particles become more susceptible to being swept out of the rings by the magnetic field, or by passing moons. At the same time, new material might be added to the rings by impacts on Saturn's moons. Every time a meteoroid hits one of the icy moons, it kicks up a spray of ice particles, and some of those particles might escape from the moon and join the rings. The rate of this process depends on the flux of meteoroids in the Saturn system, which probably varies over time as Saturn moves through different regions of the solar system and encounters different populations of debris. It's also possible that the rings could be replenished catastrophically by a major impact or by the breakup of a moon. If a moon were to be shattered by a collision or torn apart by tidal forces, The resulting debris could add a huge amount of material to the rings all at once, potentially making them brighter and more extensive than they are now. This kind of event might happen only once every few 100 million years, but when it does, it could reset the clock on the ring's lifetime. Another factor that could affect the future of the rings is the gradual evolution of Saturn's rotation and magnetic field. Saturn spins very fast. It completes one rotation in just over 10 hours, and this rapid rotation affects the shape of the planet and the structure of its magnetic field. Over billions of years, Saturn's rotation might slow, down due to tidal interactions with its moons, and this could change the way the magnetic field interacts with the rings and the way material is transported between the rings and the atmosphere. In the very long term, the rings might not survive at all. If the loss rate exceeds the input rate, the rings will eventually be depleted and Saturn will lose its most iconic feature. On the other hand, if new rings can form from time to time through moon breakup or major impacts, then Saturn might always have rings, even if the specific configuration changes over time. We might be living during a period when Saturn happens to have particularly bright and extensive rings, or we might be seeing a typical state that Saturn has maintained for much of its history. Without more data, it's hard to say for sure. What we can say is that the rings are a dynamic, evolving system, and their future is uncertain. They're not a permanent fixture of the solar system, but a transient phenomenon, something that exists for a while and then changes or disappears. This makes them all the more precious and remarkable, a reminder that even the grandest structures in nature are subject to change, and that everything we see today is just a snapshot of a much longer story. Let's think now about what the rings can teach us about physics and about the universe in general. The rings are, in many ways, a natural laboratory for studying processes that occur on much larger scales. The way particles interact in the rings is similar to the way stars interact in galaxies, or the way gas and dust interact in the disks around young stars. By studying the rings up close, we can learn about these larger-scale processes in a controlled and accessible environment. For example, the spiral density waves in Saturn's rings are very similar to the spiral arms in galaxies. In both cases, the waves are created by gravitational interactions, and they propagate through a disk of material, creating patterns that rotate and evolve over time. By studying how these waves behave in the rings, where we can see them in great detail and measure their properties precisely, we can test theories about how spiral arms form and persist in galaxies, where the scales are much larger and the observations are much more difficult. The rings also provide insights into the process of accretion, which is how planets and moons form from smaller pieces. In the rings, we can see particles colliding, sticking together temporarily, and then breaking apart again. We can measure how these processes depend on the size and speed of the particles, on the temperature and composition of the material, and on the gravitational environment. All of this information helps us understand how planets formed in the early solar system, when the space around the young sun was filled with a disk of gas and dust that gradually coalesced into the planets we see today. The rings are also a testing ground for ideas about chaos and order in dynamical systems. The motion of individual particles in the rings is, in principle, completely deterministic. If you know the position and velocity of a particle at one time, you can calculate where it will be at any future time. But in practice, the motion is so sensitive to small changes that it becomes effectively unpredictable. A tiny nudge from a collision or a gravitational interaction can send a particle on a completely different path, and over time, the cumulative effect of all these small nudges makes the system chaotic. And yet, despite this chaos at the level of individual particles, the rings as a whole show remarkable order and structure. The gaps and divisions are sharp and well defined. The spiral density waves are regular and periodic, and the overall appearance of the rings is stable over timescales of years or even decades. This coexistence of chaos and order is a fundamental feature of many complex systems, from the rings of Saturn to the weather on Earth to the behavior of financial markets, and studying the rings helps us understand how order can emerge from chaos. Now let's take a moment to appreciate the sheer beauty of the rings from an aesthetic perspective. There's something deeply satisfying about the elegance and simplicity of the ring structure. The rings are just particles following orbits, governed by gravity and shaped by collisions, but the result is a form that's both simple and intricate, both regular and varied. The rings have a kind of minimalist beauty, like a piece of abstract art where the power comes from the purity of the form. the colours of the rings add to their beauty. While the rings are mostly white and grey, there are subtle variations in tone and hue that create depth and interest. Some regions are almost pure white, gleaming in the sunlight, while others have a slightly warmer tone, hinting at the presence of impurities or different types of ice. In backlit images, the rings take on a golden or amber glow, with light streaming through the gaps and creating halos around the denser regions. The play of light and shadow, the contrast between bright and dark, the delicate gradations of tone, all of these contribute to the visual impact of the rings. There's also a certain poetry to the rings, a sense of grace and motion that comes from the way they turn around Saturn. The rings are not static, they're in constant motion, with particles orbiting at different speeds and creating waves and ripples that propagate through the system. But the motion is so smooth and so slow, at least from our perspective, that it looks almost like a dance, a choreographed performance where every particle knows its place and moves in perfect harmony with its neighbours. The rings also have a kind of fragility that makes them poignant. They're so thin and delicate, and they're constantly being eroded by collisions and by material falling into Saturn. They might not last forever, and in cosmic terms they might be gone, in the blink of an eye. This transience makes them all the more valuable, a reminder to appreciate beauty while it lasts and to recognise that everything in the universe is temporary. Let's end by bringing things back to a human scale, thinking about what the rings mean to us and why they matter. The rings of Saturn have fascinated people for centuries, ever since they were first glimpsed through early telescopes. They've inspired artists and poets, scientists and dreamers, and they've become one of the most iconic images in all of astronomy. When you see a picture of Saturn with its rings, you immediately recognise it, and you feel a sense of wonder and awe. Part of the appeal is the sheer alienness of the rings. There's nothing like them on Earth, nothing in our everyday experience that prepares us for the sight of a giant planet surrounded by a shining disk of ice. The rings remind us that the universe is full of wonders, full of things that are strange and beautiful and beyond our imagination. They expand our sense of what's possible and challenge us to think beyond the familiar. But the rings also have a kind of accessibility. Unlike distant galaxies or black holes, the rings are something we can actually see and study in detail. We've sent spacecraft to visit them, we've taken close-up pictures, and we've measured their properties with precision. We can understand how they work, at least in broad terms, using the same physics that governs motion and gravity on Earth. The rings are exotic, but they're not incomprehensible, and that makes them a perfect subject for exploration and discovery. The rings also connect us to the history of science, and to the long tradition of observation and inquiry that has brought us to our current understanding of the universe. When Galileo looked at Saturn through his telescope and saw something strange but couldn't quite make out what it was, he was taking part in the same process of discovery that continues today. Each generation of scientists is built on the work of those who came before, using better instruments and better theories to peel back the layers of mystery and reveal the rings in ever greater detail. And the story isn't over. There's still a lot we don't know about the rings, still questions to answer and mysteries to solve. How old are they? How did they form? How long will they last? What can they tell us about the early solar system and about the processes that shape planetary environments? Every new observation, every new mission brings us closer to the answers, but there's always more to learn. For now, though, we can simply rest in the knowledge that the rings are there, turning slowly around Saturn, catching the sunlight and scattering it back into space. They're a reminder of the beauty and complexity of the natural world, of the way simple rules can create intricate patterns, and of the deep connection between motion and gravity, between chaos and order. They're a source of wonder and inspiration, a testament to the power of curiosity and the joy of discovery. As you drift off to sleep tonight, you can picture the rings in your mind, pale and bright against the darkness of space, each particle following its own quiet path, each one part of a larger whole. You can imagine yourself floating among them, weightless and peaceful, watching the slow turn of the system and feeling the gentle pull of gravity. You can let the image fill your mind, pushing out all the worries and distractions of the day, and you can sink into the calm, steady rhythm of the orbits. The rings don't rush, and neither do you. There's no hurry, no pressure, no need to do anything but rest. The particles are content to orbit forever, and you can be content to let go, to relax, to drift into sleep. Your thoughts can become like the particles, light and separate, each one floating on its own path, gently bumping into others and bouncing away, until they all settle into a quiet, harmonious pattern. Take a slow breath in, filling your lungs with calm, and then let it out slowly, releasing any tension. Imagine that with each breath you're becoming lighter, more relaxed, more like the ice particles drifting in the rings. You're held in the gentle embrace of gravity, not falling but floating, moving in a perfect circle that brings you around again and again to the same peaceful place. The rings are still there, shining in the sunlight, and they'll be there tomorrow and the next day and for millions of years to come. They don't need you to watch them or think about them. They're fine on their own, turning in their quiet orbits. And you're fine too, safe and warm, ready to rest, ready to let go of the day and drift into sleep. So let yourself go now. Let your mind become light and airy. Let your body sink into the bed. Let the images of the rings fade into a soft, comfortable darkness. You don't need to think anymore. You don't need to analyze or understand. You just need to be, to exist in this moment, to rest in the knowledge that everything is all right. The rings are orbiting, your breath is flowing, and sleep is coming, gentle and inevitable, like the slow turn of particles around a giant planet. You're part of the same universe, following the same laws, held in the same balance of forces, and as the rings drift through space, you drift through sleep, peaceful and still, until the morning light brings you back again. The next story is about to begin. Please relax and enjoy.